Imagine hurling a phono-needle at a revolving disc and seeing it settle flawlessly into the track. You would then ride that spiral for precisely one circuit before lifting it away into the void. The mathematical likelihood of such an event borders on zero. And yet, 3I Atlas has accomplished this very feat with our entire solar system, threading a cosmic needle with retrograde exactitude to perform a grand tour that bypasses hazardous gravitational encounters while preserving ideal observational geometry. Within a cosmos ruled by chaos and coincidence, such precision feels nearly deliberate. I invite you to settle in as we investigate whether we are observing the universe's most unlikely accident or its most refined design. Part 1. Was the trajectory of 3I Atlas selected? After 1A Oumuamua left us stunned in 2017 and 2I Borisov came after it in 2019, I thought we had a grasp of what these celestial visitors might resemble. I was mistaken. On July 1, 2025, telescopes located in Chile spotted something remarkable. An object traveling at 57,000 kilometers per second, swift enough to orbit Earth in fewer than 12 minutes, was nearing our Sun on what astronomers term a hyperbolic trajectory. In plain language, this object was not constrained by our star's gravity. It originated from another place, and it is returning to another place. But this is where the narrative becomes compelling. This interstellar traveler, which was designated 3I Atlas, was not merely tumbling through space on some arbitrary course. On the contrary, it seemed to be gliding along the plane of our solar system. This is the same unseen disk where Earth, Mars, Jupiter, and every other planet orbit. Yet it was moving in the completely opposite direction, akin to a motorcyclist speeding backward on a motorway, holding perfect lane discipline as all other traffic streams forward. The exactness of it was disquieting. With an inclination of 175 degrees, 3I Atlas fell short of a perfect retrograde alignment with our planetary plane by a mere 5 degrees. In the boundless expanse of space, where bodies can approach from virtually any direction, what are the chances of such meticulous geometry? As astronomers charted its course, additional peculiarities came to light. The object was set to swing past Mars at just 1/5 of an astronomical unit, approximately 19 million miles, close enough for a brief wave, but not near enough for any substantial gravitational effect. Next, it would pass Venus at 6/10 of an AU. Then, after circling the Sun at its nearest point on October 29th, it would pass by Earth at 1.8 astronomical units, roughly 270 million kilometers away. Finally, a more remote rendezvous with Jupiter would occur in March of 2026. It reads like a travel plan, a grand tour of the inner solar system, meticulously arranged to prevent getting too near to any one world, while being positioned to see them all. But what is perhaps most fascinating is that 3I Atlas timed its arrival to align with what astronomers refer to as solar conjunction. Throughout its closest pass to our star, the object would be concealed behind the Sun from our terrestrial vantage point, rendering detailed observations almost impossible. This is a convenient happenstance for an object that supposedly lacks any agenda. Unlike Oumuamua, which left us scratching our heads due to its enigmatic acceleration and total absence of visible outgassing, 3I Atlas made its presence known with all the indicators of a conventional comet. Images from the Hubble Space Telescope showed a luminous coma, the hazy shell of gas and dust that appears when ice sublimates in the solar wind. There was even a subtle tail, precisely what one would anticipate from a piece of dirty ice visiting from the frigid depths between stars. Still, something felt amiss. Initial observations indicated that most of the brightness was concentrated ahead of the object's path of travel, while that telltale tail persisted in being stubbornly faint. Some scientists started to whisper about forward scattering effects and atypical dust dynamics. Others questioned if they were seeing something unparalleled, an artificial object crafted to imitate a natural comet. The velocity itself communicates a story. At 57 to 58 kilometers per second relative to the Sun, 3I Atlas travels with the speed characteristic of objects in our galaxy's stellar vicinity. It is not the blistering pace one might expect from something intentionally propelled across interstellar voids, but neither is it suspiciously sluggish. It is the Goldilocks of cosmic velocities, not too rapid, not too slow, but perfectly calibrated to merge with the natural background hum of galactic movement. Size estimations fluctuated wildly during those initial weeks. Early accounts proposed a behemoth up to 20 kilometers wide, vast enough to contain entire cities if it were hollow. But as Hubble's keen vision pierced through the enveloping coma, a different reality took shape. The nucleus seemed to be significantly smaller, maybe only a few kilometers in diameter, and possibly even less than a kilometer. While still considerable, it was hardly the colossal mothership that early observations had suggested. The timing of the appearance of 3I Atlas feels meaningful in ways I am only starting to grasp. I live in a period when astronomical surveys are more sensitive than they have ever been. Initiatives such as the Asteroid Terrestrial Impact Last Alert System, ATLAS, scan the heavens nightly, created to detect potentially hazardous asteroids but perfectly situated to find interstellar interlopers. The Vera Rubin Observatory, which will soon be operational, promises to identify dozens of these visitors over the next decade. Are we merely becoming more adept at spotting what has always been present? Or is something dispatching more visitors in our direction? The scientific community is approaching 3I Atlas with a caution that stems from hard-won experience. Oumuamua taught us that these objects can defy our assumptions in ways that challenge our comprehension of physics. Some mainstream astronomers believe 3I Atlas will turn out to be precisely what it seems: an interstellar comet adhering to the foreseeable laws of celestial mechanics, with any seeming irregularities explained by observational bias and the peculiarities of orbital dynamics. However, a vocal minority contends that we should keep more unconventional possibilities in consideration. After all, if a sophisticated civilization desired to examine our solar system, how would they go about it? Would they dispatch an overt artificial probe that announces alien technology to anyone with a telescope? Or would they engineer something that looks exactly like the type of natural debris we would anticipate from interstellar space? This question lingers over our observations like a cosmic Rorschach test. Do I perceive patterns and purpose because they genuinely exist, or because my pattern-seeking mind insists on finding a narrative where only chaos resides? When 3I Atlas vanishes behind the Sun during its nearest approach, am I witnessing meticulously planned reconnaissance or merely the predictable geometry of orbital mechanics? Both NASA and the European Space Agency have released statements stressing that 3I Atlas presents no danger to Earth. The closest it is projected to come is still over 4 times the distance to our Moon, a comforting margin of safety. Yet safety was never the primary issue. The issue is far more elemental. Are we alone in the universe, or are we being observed? As 3I Atlas proceeds on its path toward perihelion, every observation yields new data and new questions. Spectroscopic analysis could uncover the chemical fingerprints that differentiate a natural comet from something more exotic. Thermal imaging might pick up heat signatures inconsistent with passive solar warming. Radio telescopes are listening for any signal, no matter how faint, that could indicate an artificial origin. The object will be observable through September 2025 before the Sun's glare makes tracking unfeasible. Then, in early December, it will reappear from conjunction, potentially altered by its close pass by our star. Comets frequently appear different after their perihelion passage, brighter, more active, and sometimes even breaking apart under thermal strain. What I see in those December observations may finally resolve the question that has haunted us since that July discovery. Was the trajectory of 3I Atlas chosen, or did we simply choose to notice it? In a universe where intention and coincidence can appear remarkably alike, the difference matters more than I might wish to admit. Part 2. The Discovery. Atlas spots an interstellar interloper. Sometimes the most phenomenal discoveries start with the most commonplace observations. On the evening of July 1, 2025, a pair of robotic telescopes at the Atlas facility in Rio Hueso, Chile, were engaged in their nightly routine, methodically sweeping the sky for anything that moved. Their task is ordinary but essential: to locate asteroids that might pose a threat to Earth before they locate us. The computers almost instantly flagged Object 11 PAL 3Z as atypical. It was not because it appeared especially exotic, just a dim speck of light moving across the starfield like countless others. But this particular speck was traveling in the incorrect direction, at the incorrect speed, and with the incorrect orbital properties for anything native to our solar system. Within 24 hours, the Minor Planet Center in Cambridge, Massachusetts, the official hub for discoveries of small bodies, had verified what the automated systems had suspected. This was not another common asteroid or comet. The object, designated 11P L3s, was moving on a hyperbolic trajectory with an eccentricity of approximately 6.1. In the field of orbital mechanics, any object with an eccentricity exceeding 1 is unbound, which means it will never come back. This visitor was just passing by, not taking up residence. The official announcement was made on July 2nd. Humanity had located its third confirmed interstellar object. The designations followed with bureaucratic exactness. 3I Atlas for the Interstellar Catalog, C 2022-N1 for the Comet designation, acknowledging the accumulating proof of outgassing activity that set it apart from its mysterious forerunner, Oumuamua. However, the timeline of the discovery was not quite so straightforward. As is frequently the case in astronomy, the discovery was, in fact, a rediscovery. Searches of archives showed that both Atlas telescopes and the Zwicky Transient Facility had taken images of the object as far back as June 14th, and perhaps even earlier. These recovery observations are invaluable to asteroid hunters. They push the observational arc further back in time, significantly enhancing orbital calculations and forecasts. The figures were astounding. At the time of its discovery, 3I Atlas was already 4.5 astronomical units from the Sun, about the same distance as Jupiter's orbit, and was moving at 61 kilometers per second. That equates to 137,000 miles per hour, quick enough to traverse the United States in under 2 minutes. Even more impressively, when astronomers determined its velocity relative to the Sun after factoring in our star's gravitational pull, they found it was traveling at 57 to 58 kilometers per second. This is exactly the type of speed one would anticipate from an object that came from interstellar space and was drawn in by our solar system's gravitational well. The worldwide astronomical community mobilized with the kind of synchronized efficiency that makes one appreciate living in the 21st century. Within mere hours of the Minor Planet Center's circular reporting the discovery, observatories on 6 continents were directing their instruments toward the specified coordinates. Amateur astronomers collaborated with professional groups in a global effort to monitor the object's brightness, location, and any indications of activity. The Virtual Telescope project in Italy promptly set up public viewing events, broadcasting live images as 3I Atlas slowly moved against the backdrop of stars. Radio telescopes commenced listening for any signals. Space agencies put out the first of numerous press releases, carefully striking a balance between enthusiasm and scientific prudence. NASA's communications were particularly cautious, underscoring 3 primary points. Yes, this object was truly interstellar. No, it presented no danger to Earth. And yes, it offered an unparalleled chance to examine material from another star system. The European Space Agency reiterated these sentiments, remarking that their forthcoming Comet Interceptor mission, intended to rendezvous with a pristine comet from the outer solar system, could act as a model for future encounters with interstellar visitors. Early estimations of its size turned out to be wildly imprecise, varying from a few hundred meters to several kilometers in diameter. The difficulty is in differentiating the nucleus itself from the enveloping coma of gas and dust. Without knowledge of the object's albedo, how much sunlight it reflects versus absorbs, and without comprehending the role of outgassing in its total brightness, astronomers were, in essence, making educated guesses. This ambiguity resulted in some rather dramatic early headlines. A number of media outlets announced a potentially enormous object up to 20 kilometers across, hurtling through our solar system. The truth, as observations from the Hubble Space Telescope would later show, was more modest, yet no less captivating. The mix-up originates from a basic challenge in observing asteroids and comets. When one views these objects through a telescope, one is not seeing the solid surface in the way one might see Mars or Jupiter. Instead, one is viewing scattered sunlight from both the nucleus and any surrounding dust or gas. To separate these components requires complex modeling and numerous observations at various wavelengths and phase angles. For 3 Atlas, this issue was magnified by its clear activity. In contrast to Oumuamua, which exhibited no visible signs of outgassing, this new visitor showed a distinct coma from the moment it was found. That hazy envelope of sublimated ice and released dust makes accurate size measurements nearly impossible without in-depth analysis. The media focus was swift and powerful. CNN featured segments that compared 3I Atlas to Oumuamua and speculated on its origins. The Guardian released articles explaining interstellar objects and what their makeup might reveal about other planetary systems. Science journalists worked diligently to render orbital mechanics into understandable terms for an intrigued public. Yet what the discovery disclosed about our own abilities was perhaps more intriguing. The finding of 3 Atlas showed just how much our astronomical infrastructure had advanced since Oumuamua's surprise arrival 8 years prior. We had better surveys, quicker follow-up networks, and more advanced analysis tools. We were no longer taken completely by surprise by interstellar visitors. The Atlas system itself warrants special recognition. Funded chiefly to locate potentially dangerous asteroids, its 4 telescopes, 2 in Hawaii, 1 in Chile, and 1 in South Africa, act as a sort of early warning system for threats from space. That this network also functions as humanity's primary line of detection for objects from other star systems is a fortunate result of geometry and timing. As July gave way to August, the observation campaign grew more intense. Ground-based telescopes monitored the brightness and color of 3I Atlas, searching for clues as to how its activity might change as it drew nearer to the Sun. Space-based instruments like Hubble readied for detailed imaging sessions that would uncover the object's true character. The discovery had settled one vital question. We were indeed seeing humanity's 3rd confirmed interstellar visitor, but it had posed dozens more. Where exactly had this object come from? What was its internal makeup? How large was its nucleus beneath that expanding coma? And, perhaps most compellingly, why did its trajectory seem to trace such a precise route through our planetary system? Amateur astronomers and professional researchers alike braced themselves for the months to come, aware that 3 Atlas would grow brighter as it approached the Sun, possibly unveiling secrets about the formation and evolution of planetary systems light years away from our own. The discovery phase was complete. Now, the far more difficult task of comprehending what we had found began. The night sky had presented another puzzle, concealed within the deceptive simplicity of a moving point of light. As telescopes across the globe maintained their patient vigil, one thing was certain. 3I Atlas was poised to teach us something new about the universe we thought we understood. Part 3. A rare visitor, only the third of its kind. Suppose meteorites were as infrequent as winning a lottery jackpot. One could live an entire life without ever hearing of a single verified instance, much less seeing one. This is essentially the circumstance we were in with interstellar objects until quite recently. Throughout all of human history, we had never knowingly seen a single visitor from another star system journey through our cosmic vicinity. Then, in October 2017, everything shifted with Oumuamua. The name translates to scout or messenger in Hawaiian, and it certainly fulfilled its role as a harbinger of things we did not anticipate. Oumuamua presented itself with credentials that shouted, "Not from this area," a hyperbolic orbit, a reddish hue, and an elongated form unlike anything in our solar system's collection of asteroids and comets. However, what truly riveted scientific focus was not what it was, but what it did. As Oumuamua rounded the Sun and started its voyage back into interstellar space, astronomers observed something without precedent. The object was accelerating, not significantly, but measurably, in a manner that could not be accounted for by gravitational forces alone. The acceleration was slight, about 17 meters per second integrated over its entire solar passage, but it was definite, and it was directed away from the Sun. This non-gravitational acceleration ignited a scientific discussion that persists to this day. The conventional explanation centers on outgassing, the concept that as Oumuamua warmed near the Sun, subsurface ice sublimated, creating minuscule jets that propelled the object forward. The issue was, no one could detect any proof of this outgassing. No coma, no tail, no spectroscopic evidence of water or other volatile substances. It was like observing a car accelerate without the sound of its engine. More unconventional theories surfaced. Perhaps Oumuamua was mainly composed of hydrogen ice, which would sublimate without a trace. Or maybe it was, in fact, a thin, flat object being propelled by solar radiation pressure, similar to a natural light sail. This latter theory, promoted by Harvard's Avi Loeb, raised the prospect that Oumuamua might be artificial, humanity's initial encounter with technology from another civilization. 2 years after that, 2I Borisov arrived and acted as a sort of palate cleanser. Here was an interstellar object that acted precisely as textbook comets are supposed to act. It formed a stunning coma and tail as it neared the Sun. Spectroscopic analysis showed familiar signs of water vapor, carbon monoxide, and other volatile compounds. It even broke apart near perihelion, a typical outcome for comets under thermal stress. But 2I Borisov had its own set of surprises. Chemical analysis indicated it was unusually abundant in carbon monoxide compared to comets from our own outer solar system. This was not necessarily out of the ordinary. CO can be more prevalent in extremely cold regions, but it implied that wherever Borisov came from, the conditions were different from the icy domain where our own Oort cloud comets were born. Now, 3I Atlas offers a third data point in my developing comprehension of interstellar visitors. Like Borisov, it displays clear indications of cometary activity, the comforting glow of a coma and the faint streak of a dust tail. Yet, like Oumuamua, it poses questions that defy my assumptions about what is considered normal for objects from other star systems. The scarcity of these findings until recently was not necessarily because interstellar objects were infrequent. Current projections indicate that at any given time there could be thousands or even tens of thousands of interstellar objects transiting our solar system. The challenge was that they are generally small, dark, fast-moving, and very distant, precisely the kind of targets that conventional asteroid surveys were ill-suited to find. The situation changed with the advent of automated wide-field sky surveys, primarily created to locate potentially hazardous asteroids. Projects such as Linear, Neowise, Atlas, and the Catalina Sky Survey were not specifically searching for interstellar visitors, but their advanced detection algorithms and swift follow-up capabilities made such discoveries almost certain. The Vera Rubin Observatory, now being built in Chile, is set to transform this area with its 8.4-meter primary mirror and 3.2 gigapixel camera. Rubin will scan the entire visible sky every few nights, potentially finding 6 to 50 interstellar objects annually, depending on their size, distribution, and activity levels. What appears rare now may become commonplace within a decade. This statistical fact offers a significant perspective on assertions that 3I Atlas is somehow special or targeted. When one increases the detection rate by orders of magnitude, one is bound to find objects with unusual traits simply due to larger sample sizes. Some will have orbital geometries that appear meticulously planned. Others might exhibit unexpected spectroscopic signatures or variations in brightness. The crucial task is to differentiate between what is unusual because it is interesting and what is unusual because it is artificial. The public's fascination with these discoveries generates its own feedback mechanisms. Media reports on interstellar objects tend to emphasize their mysterious or anomalous features, often overlooking more ordinary explanations. This is not necessarily detrimental. Wonder and curiosity are the engines of scientific investigation, but it can result in hasty conclusions about the importance of specific observations. Social media amplifies these tendencies. A paper suggesting that an interstellar object's trajectory indicates artificial guidance can become viral before peer review has had an opportunity to spot methodological errors or alternative interpretations. The speed at which information spreads often surpasses the measured pace of scientific confirmation. Nevertheless, there is immense scientific worth in every interstellar visitor, regardless of whether it is proven to be natural or artificial. Each object contains information about the stellar system where it originated. Chemical signatures, isotope ratios, structural features that cannot be acquired in any other manner. They are like geological specimens from worlds we will never reach, delivered to our doorstep at no cost. For 3 Atlas in particular, the blend of visible activity and accessible geometry makes it especially valuable. Unlike Oumuamua, which was found as it was already leaving and could only be observed for a few weeks, 3I Atlas was detected months before its closest approach to the Sun. This prolonged observation period permits detailed spectroscopic campaigns, thermal modeling, and precise astrometry that can unveil subtle details about its composition and structure. The object also functions as a test case for our institutional reactions to unusual discoveries. How rapidly can the global astronomical community coordinate observations? How well can we convey uncertainty to the public without either brushing aside intriguing possibilities or promoting baseless speculation? What occurs when tentative scientific hypotheses clash with our cultural narratives about contact with extraterrestrial intelligence? These lessons are important because 3I Atlas will not be our final interstellar visitor. The Rubin era will bring us dozens more, each potentially possessing its own unique traits and challenging our understanding in different ways. Some may be completely ordinary chunks of ice and rock. Others might show properties that stretch the limits of what we consider natural. The rarity of interstellar objects is already fading into history. What remains rare is our experience in studying them methodically and our wisdom in interpreting our findings. 3I Atlas represents not just our third confirmed interstellar visitor, but our third chance to practice the delicate art of scientific inquiry under intense public observation. As we get ready for a future where such discoveries are routine rather than exceptional, the lessons we learn from 3I Atlas may be as valuable as any specific scientific data it yields about its own nature and origin. Part 4, The Trajectory Puzzle. Geometry, speed, and flybys. Imagine a cosmic billiards table where someone has just pulled off the most unlikely shot in history. The cue ball, our 3I Atlas, comes in from the darkness beyond the table's edge, moving at exactly the right angle and velocity to glide along the felt surface, brush past several other balls with mathematical exactness, and then roll off the opposite side to vanish into the void. The precision is so extraordinary that I find myself asking, was this shot planned? In the language of orbital mechanics, 3I Atlas is on what astronomers describe as an extremely hyperbolic trajectory with an eccentricity of roughly 6.1. To grasp what this implies, consider the distinction between a circle, an ellipse, and a hyperbola. Planets move in ellipses with eccentricities below 1. Earth's orbit has an eccentricity of just 0.017, which makes it almost circular. A flawless circle has an eccentricity of exactly 0, whereas a parabola, the mathematical line between bound and unbound motion, has an eccentricity of precisely 1. Any object with an eccentricity greater than 1 travels along a hyperbolic path, meaning it is moving too swiftly for the Sun's gravity to hold it permanently. 3I Atlas, with its eccentricity of 6.1, is so unbound that it will depart our solar system traveling nearly as fast as it arrived, having only borrowed a slight amount from the Sun's gravitational well. But it is the geometry of this hyperbola that is causing some surprise. The object is approaching our solar system from the general vicinity of Sagittarius, toward the center of our galaxy, which might sound impressive until one realizes that this is a fairly typical direction for interstellar objects, given our galaxy's rotation and stellar dynamics. There is nothing particularly noteworthy about that trajectory, apart from a single detail. 3I Atlas holds an inclination of approximately 175 degrees relative to the ecliptic plane, that unseen disk where all the planets orbit. This signifies that it is moving in a retrograde direction, counter to the motion of the planets. But here is the vital point. It is only 5 degrees away from a perfect alignment with that plane. Consider this from a geometric standpoint. In three-dimensional space, an object can arrive from practically any direction, up, down, sideways, at any conceivable angle. The ecliptic plane constitutes a minuscule fraction of all potential orientations, yet 3I Atlas strikes it almost perfectly. It is comparable to tossing a frisbee into a parking structure and having it somehow finish up sliding along the floor instead of striking the ceiling, walls, or any of the myriad other available surfaces. The series of planetary encounters introduces another dimension to this geometric riddle. On October 3, 2025, 3I Atlas will pass within 0.19 astronomical units of Mars, about 19 million miles, which may seem distant but is a relatively close encounter in solar system terms. On November 3, it will sweep by Venus at 0.65 astronomical units. Then, after swinging around the Sun at its closest point on October 29th, at approximately 1.36 to 1.4 astronomical units, just inside Mars's average orbital distance, it will proceed outward for an Earth flyby on December 19th at 1.8 astronomical units. Finally, on March 16th, 2026, it will meet Jupiter at 0.36 astronomical units, about 34 million miles from the giant planet. Each of these distances is substantial enough to prevent any significant gravitational interaction. 3I Atlas is not using these planets for gravity assists in the manner that interplanetary spacecraft do. It is not appropriating orbital energy to alter its course. The encounters are more like cosmic near misses, close enough to be noteworthy, far enough to be safe, and precisely spaced to create what almost looks like a pre-planned schedule. The velocities involved are just as extraordinary. At its discovery, 3I Atlas was moving at approximately 61 kilometers per second relative to the Sun. As it nears perihelion, gravitational acceleration will increase this to nearly 68 kilometers per second. But perhaps most importantly, its velocity relative to the local galactic neighborhood, what astronomers call V infinity, is 57 to 58 kilometers per second. This is not the blistering speed one might anticipate from an artificial probe sent between star systems. It is exactly the type of velocity one would forecast for debris that originated in another stellar system and was caught by our Sun's gravitational influence. Being too fast to be natural would actually appear suspicious. Being too slow would also be peculiar. 3I Atlas moves at exactly the Goldilocks velocity, not too fast, not too slow, but just right to blend in with the natural background of interstellar material. Still, there is something disquieting about the timing. As 3I Atlas approaches its nearest point to the Sun, it will pass through what astronomers term solar conjunction. The object will be positioned behind the Sun as seen from Earth, which will make detailed observations nearly impossible during its most active phase. This is not uncommon for objects with perihelia around 1 to 2 astronomical units, but it certainly complicates matters for scientists attempting to study the visitor during its most interesting period. The Hubble Space Telescope has created stunning trajectory visualizations that show the path of 3I Atlas as a graceful hyperbola weaving through the solar system. These diagrams display the ballistic precision of celestial mechanics, how gravity shapes motion over millions of miles with mathematical perfection. But they also underscore the seeming deliberateness of the path, the way it appears crafted to offer glimpses of multiple worlds without getting close enough to any of them to be captured or diverted. Observational uncertainties contribute another facet to the puzzle. While the overall shape of the trajectory is well known, the exact distances and timings still have error margins. The stated perihelion distance of 1.36 to 1.44 astronomical units reflects current uncertainties in the orbital solution. Likewise, the various planetary encounter distances are predictions based on current trajectory calculations, not predetermined destinations. This uncertainty is both vexing and significant. It is vexing because it keeps us from making definitive claims about the object's path. It is significant because it reminds us that what seems like precision in celestial mechanics can actually be a reflection of the limits of our observational tools rather than genuine cosmic choreography. Further astrometric observations are continuing to refine these orbital elements. Each new position measurement helps to reduce the error ellipses around predicted future locations. By the time 3I Atlas reaches perihelion, we will have a much more precise understanding of exactly where it is headed and when it will arrive. The trajectory brings up fundamental questions about the nature of coincidence in the universe. How often do random journeys through interstellar space result in paths that look this structured? Is apparent design an unavoidable result of enhanced detection capabilities, where we notice the unusual cases precisely because they are unusual? Or does it point to something more deliberate? As 3 Atlas carries on with its precisely choreographed dance through our solar system, these questions become more than just academic ponderings. They challenge my understanding of what serves as evidence for intelligence in a universe where natural processes can generate patterns that appear remarkably purposeful. The geometry is undeniable. Its interpretation remains tantalizingly uncertain. Part 5. Comparing to Oumuamua, a different flavor of weird. If interstellar objects were individuals appearing at one's door uninvited, Oumuamua would be the enigmatic stranger in a trench coat who leaves no evidence, whereas 3I Atlas would be the talkative neighbor who seems entirely normal until one realizes they know a bit too much about one's daily habits. Both are disquieting, but in entirely distinct manners. Oumuamua exploded into my consciousness in October 2017 as humanity's first confirmed interstellar visitor and immediately shattered every rule I thought I understood about how such objects ought to behave. The strangeness began with its shape, spectacularly elongated, perhaps 10 times as long as it was wide, and tumbling end over end like a cosmic cigar or needle. Nothing in our solar system resembles Oumuamua, which instantly prompted questions about how such an object could arise naturally. But the true enigma was its movement. As Oumuamua rounded the Sun and commenced its journey back to interstellar space, precise tracking uncovered something unprecedented. The object was accelerating away from the Sun in a manner that could not be explained by gravity alone. The acceleration was minor, about 17 meters per second in total, but it was quantifiable, consistent, and completely unforeseen. For comets, such non-gravitational acceleration is commonplace. As these dirty snowballs near the Sun, subsurface ice begins to sublimate, forming jets of gas that push the comet around like miniature rocket engines. But Oumuamua displayed no visible indications of this outgassing activity. No coma, no tail, no spectroscopic signatures of water vapor or other volatile substances. It was accelerating like a comet while looking like an asteroid. The scientific community met this with inventive explanations. Perhaps Oumuamua was composed chiefly of hydrogen ice, a type of frozen hydrogen that would sublimate without a trace, leaving no detectable signature in our telescopes. Maybe it was coated with an organic layer that prevented us from seeing the underlying ice, or possibly it was expelling material from its sides rather than creating the sunward-pointing jets typical of active comets. The most unconventional hypothesis originated from Harvard's Avi Loeb, who proposed that Oumuamua might actually be artificial, a light sail propelled by solar radiation pressure rather than outgassing. This would necessitate the object being extremely thin and flat, more akin to a cosmic pancake than the elongated needle implied by its brightness fluctuations. Loeb contended that while this interpretation might seem improbable, it actually aligned with the observations better than any of the suggested natural explanations. Tao I. Borisov, discovered in August 2019, served as a kind of cosmic palate cleanser after Oumuamua's enigmas. Here was an interstellar object that behaved precisely as astronomy textbooks indicated comets should behave. As it neared the Sun, it developed a spectacular coma and tail. Spectroscopic analysis revealed familiar signatures of water vapor, carbon monoxide, and cyanide, the standard array of volatiles expected from sublimating ice. Borisov even fragmented as it rounded the Sun, breaking apart under thermal stress in a display that would have looked perfectly normal had it been a comet from our own Oort cloud. The only unusual trait was its chemistry, specifically high concentrations of carbon monoxide compared to typical solar system comets. But this difference was readily explained by formation in a colder environment around a different star. Now, 3I Atlas presents us with a third model of interstellar behavior, merging elements from both its predecessors while introducing new puzzles of its own. Like Borisov, it shows clear signs of cometary activity from the moment of discovery. Hubble Space Telescope images reveal a well-developed coma and a faint anti-solar tail, exactly what one would expect from sublimating ice-releasing dust into space. But the activity pattern is subtly different. Early observations showed most of the object's brightness concentrated in a sunward direction, ahead of its motion, with the traditional anti-solar tail remaining relatively weak. This forward-scattering brightness pattern is not impossible for a natural comet, but it is unusual enough to raise questions about the dust's properties and distribution. Size constraints tell another intriguing story. Initial reports suggested 3I Atlas might be enormous, potentially up to 20 kilometers in diameter. But as Hubble's sharp vision cut through the surrounding coma, a different picture emerged. The nucleus appears to be much smaller, with current estimates suggesting a radius of less than 2.8 kilometers, possibly as small as a few hundred meters. This size revision is important because it affects calculations of dust production rates and outgassing efficiency. A smaller nucleus would need to be much more active per unit surface area to produce the observed coma, potentially indicating either unusual composition or structural properties that distinguish it from typical solar system comets. The dust mass loss rate estimates range from 10 to 120 kilograms per second, depending on assumptions about grain size distribution and density. These numbers sound impressive until one realizes that even the high end represents a tiny fraction of the object's total mass. A few kilometer nucleus could sustain such losses for thousands of years without significantly depleting its volatile reserves. Morphological analysis of the Hubble images reveals another intriguing detail. The sunward dust emission appears to originate from the day side of the nucleus, consistent with solar heating driving sublimation. This is exactly what one would expect from a natural comet. Yet the geometry creates an appearance that some observers have interpreted as unusual or potentially artificial. The spectroscopic story continues to evolve as 3I Atlas approaches the Sun and signal-to-noise ratios improve. Early attempts to detect gas signatures have yielded ambiguous results, which is not surprising given the object's distance and the inherent challenges of observing faint emission lines against the background sky. The experience with 2E Borisov reminds us that patience is essential. Many of that object's most interesting chemical signatures only became apparent during its closest solar approach. What emerges from this comparison is a pattern of increasing familiarity combined with persistent anomalies. Oumuamua was thoroughly alien, nothing like it existed in our catalogs of solar system objects. Borisov was reassuringly familiar despite its interstellar origin. 3I Atlas occupies a middle ground, obviously cometary, yet subtly different in ways that keep nagging at the edges of our understanding. The brightness evolution provides another point of comparison. Oumuamua's light curve showed dramatic variations consistent with a highly elongated, tumbling object. Borisov's brightness increased predictably as it approached the Sun, following the standard relationship expected for sublimating ice. 3I Atlas displays brightness patterns that are mostly consistent with cometary models, but with subtle deviations that have sparked debates about dust, scattering properties, and potentially unusual nucleus characteristics. Perhaps most importantly, the sequence of these three discoveries illustrates how our understanding of interstellar objects continues to evolve. Each visitor teaches us something new about the possible range of properties and behaviors we might expect from debris originating in other stellar systems. Oumuamua expanded our conception of what was possible. Borisov reassured us that familiar physics still applies. 3I Atlas suggests that the truth might lie somewhere in between, objects that are recognizably natural yet distinctly foreign. The observational challenges also differ significantly. Oumuamua was discovered when it was already outbound, providing only a few weeks of useful observations before it faded beyond detection limits. Borisov offered a more generous timeline, remaining observable for nearly a year as it made its closest approach to the Sun. 3I Atlas provides perhaps the best observational opportunity yet, discovered months before perihelion and positioned for extended monitoring through multiple phases of its solar encounter. This extended observation window allows for more sophisticated analysis techniques. While Oumuamua's mysterious acceleration had to be inferred from precise astrometry over a short-time baseline, 3I Atlas can be monitored for any signs of non-gravitational forces over many months. If the object were to display unexpected trajectory deviations, we would have much better data to distinguish between natural outgassing effects and more exotic possibilities. The public and scientific reception of these discoveries also reveals interesting patterns. Oumuamua generated intense debate precisely because it defied easy categorization. Borisov was largely welcomed as a return to normalcy, an interstellar object that behaved as theory predicted. 3I Atlas rekindles the controversy not because it is as dramatically anomalous as Oumuamua, but because its subtle unusualities leave room for multiple interpretations. The lesson from this trilogy of visitors may be that interstellar objects resist simple categorization. Each carries its own combination of familiar and foreign characteristics, reflecting the diverse conditions in the stellar systems where they formed. What looked like anomalies in Oumuamua might represent normal variations within a population we are only beginning to sample. Yet the nagging questions persist. If these objects are simply natural debris from other planetary systems, why do they keep surprising us? And if there is something more intentional, why do they work so hard to mimic natural phenomena? 3I Atlas, with its combination of obvious activity and subtle anomalies, seems designed to keep us guessing, though whether by cosmic coincidence or deliberate intent remains tantalizingly unclear. Part 6. Signs of Anomalies. What looks off and what doesn't. There comes a point in every compelling mystery when one realizes the clues are pointing in two directions simultaneously. The butler possessed the means, motive, and opportunity. But so did the victim's business associate, and both of their alibis are solid. This is essentially the situation I find myself in with 3I Atlas, gathering a set of observations that could bolster either a completely natural explanation or something significantly more fascinating. Let us begin with the most visually compelling anomaly, that nearly perfect alignment with our solar system's planetary plane. With an inclination of 175 degrees, 3I Atlas is approaching in a retrograde motion, yet it remains within 5 degrees of the ecliptic. To the human eye, which is accustomed to thinking in terms of intent and design, this appears almost deliberately orchestrated. Why would a random piece of debris from interstellar space happen to arrive along the exact plane where all our planets travel? The astronomical response is more intricate than it initially seems. Survey selection biases have a critical role here. Most programs for detecting asteroids and comets focus their searches near the ecliptic, where the overwhelming majority of solar system objects are found. We are much more prone to discovering objects that traverse these well-observed regions than those that approach from high inclinations where fewer telescopes are looking. Furthermore, the ecliptic is not merely an arbitrary reference plane. It signifies the gravitational midplane of our solar system, where the combined mass of the Sun and planets establishes a kind of cosmic divide. Objects coming from interstellar space undergo subtle gravitational focusing effects that can preferentially guide them toward this plane. So, while the alignment appears suspicious, it might actually be a natural outcome of solar system dynamics. The series of planetary encounters introduces another layer of seeming deliberateness. 3I Atlas will pass Mars at 0.19 astronomical units, Venus at 0.65 astronomical units, Earth at 1.8 astronomical units, and Jupiter at 0.36 astronomical units. When arranged chronologically, this seems like a meticulously planned grand tour of the inner solar system. But orbital mechanics presents a different perspective. These are not close encounters in any gravitationally meaningful way. The object will not experience significant deflection or energy exchange from any of these planets. The missed distances are so large that 3I Atlas essentially disregards the planet's gravitational wells, staying on its predetermined hyperbolic course with only minimal disturbance. More concerning to some observers is the timing of the solar conjunction. As 3 Atlas gets to its closest point to the Sun on October 29th to 30th, it will be situated almost directly behind our star as seen from Earth. This makes detailed observations nearly impossible during what should be the object's most active phase, when heating effects are at their peak, and any unusual features might be most noticeable. Skeptics could contend that this timing appears convenient for something trying to evade observation. But astronomers argue that solar conjunction is an unavoidable result of orbital geometry for any object with a perihelion distance of around 1 to 2 astronomical units. It is not hiding, it is simply obeying the predictable laws of celestial mechanics. The brightness morphology offers more subtle difficulties for a straightforward interpretation. Images from the Hubble Space Telescope indicate that most of the object's luminosity is concentrated sunward, ahead of its direction of movement, with a relatively faint traditional comet tail pointing away from the Sun. This forward scattering pattern is not out of the question for natural dust, but it is uncommon enough to provoke discussion. Some commentators have proposed that this brightness distribution suggests self-luminosity, the object producing its own light rather than just reflecting and scattering sunlight. This would indeed be exceptional, potentially pointing to internal energy sources inconsistent with passive rock and ice. But the Hubble analysis team interprets the same observations as normal illumination geometry combined with the properties of forward scattering dust. Size estimations have also sparked confusion and speculation. Initial media accounts suggested a massive object, possibly 20 kilometers in diameter, large enough to contain cities if it were artificial. These estimations were based on brightness observations that did not factor in coma contamination and made conservative assumptions about surface reflectivity. As Hubble's sharp resolution started to separate the nucleus from its surrounding gas and dust envelope, a more modest reality came into view. Current models limit the nucleus radius to less than 2.8 kilometers, with some solutions indicating an object just a few hundred meters across. It is still substantial, but hardly the massive mothership that initial reports suggested. This size revision actually introduces new puzzles. A smaller nucleus would need to be remarkably active per unit of surface area to generate the observed coma brightness. Either 3I Atlas is made of unusually volatile material, or its internal structure permits more efficient outgassing than typical solar system comets. The dust production rates estimated from Hubble observations range from 10 to 120 kilograms per second, depending on assumptions about particle size distribution. While these figures sound impressive, they represent only a tiny fraction of the object's likely mass. Even a modest nucleus of a few kilometers could maintain such losses for millennia without significant depletion. Chemical analysis remains frustratingly incomplete due to the object's distance and the current constraints of spectroscopic observations. Early efforts to identify specific gas species, water vapor, carbon monoxide, carbon dioxide, cyanide, have produced ambiguous results. This lack of clear spectroscopic signatures does not prove the object is unusual. It might simply reflect the difficulties of observing faint emission lines against the background sky. The experience with 2I Borisov advises patience here. Many of that object's most interesting chemical features only became evident as it approached perihelion, and warming effects increased gas production to detectable levels. 3I Atlas may yet show distinctive compositional fingerprints as it gets closer to the Sun. Perhaps most fascinatingly, some researchers have pointed out subtle asymmetries in the object's brightness and morphology that defy easy explanation with standard comet models. The sunward dust emission seems slightly displaced from the nucleus's center, possibly indicating localized outgassing from specific surface areas rather than the more uniform activity typical of solar system comets. These morphological details are important because they could differentiate between thermal heating effects, which should produce relatively symmetric outgassing patterns, and more exotic energy sources that might create structured or directional emissions. However, interpreting such subtle features demands extremely careful calibration of instrumental effects and atmospheric distortions. The rotational state of 3I Atlas remains largely undetermined, another gap that restricts our capacity to model its activity patterns. Most comets exhibit clear periodic changes in brightness and morphology as different parts of their surfaces rotate into and out of sunlight. The lack of obvious rotational signatures could suggest either a very long rotation period, a nearly spherical shape, or a viewing geometry that minimizes the visibility of rotational effects. What I gather from this list of anomalies is a picture of an object that consistently defies simple interpretation while staying just within the realm of natural explanation. Each unusual feature has potential conventional explanations. Yet the accumulation of subtle oddities forms a pattern that keeps chipping away at the edges of scientific certainty. The crucial question becomes whether these seeming anomalies represent genuine deviations from expected behavior, or simply the unavoidable outcome of studying an unfamiliar type of object with limited observational tools. Natural phenomena can appear artificial when seen through the filter of incomplete data, and human pattern recognition systems have evolved to perceive agency in ambiguous circumstances. As 3i Atlas continues its approach toward perihelion, each new observation has the potential to either solve these puzzles through conventional comet physics or deepen the mystery by revealing characteristics that push beyond the limits of natural explanation. The anomalies are real. Their interpretation remains tantalizingly open for debate. Part 7. Natural Explanations. The Comet Playbook. Sometimes the most refined explanation is the most straightforward one, and in astronomy, that typically means calling upon the well-established physics of ice, dust, and sunlight. For all its unusual traits, 3i Atlas exhibits the fundamental characteristic that immediately classifies it as a natural object. It is actively outgassing, just as a comet should. The basic physics are simple and have been honed over decades of studying comets throughout our solar system. As 3i Atlas nears the Sun, solar radiation warms its surface, causing subsurface ice to sublimate directly from a solid to a gas. This escaping vapor brings with it tiny dust particles that were mixed with the ice, forming the distinctive coma, that hazy envelope of gas and dust that envelops the nucleus and makes it visible from immense distances. Observations from the Hubble Space Telescope confirm that this process is happening exactly as theory foresees. The images show a well-formed coma with clear signs of sunward dust emission and a faint anti-solar tail. The sunward emission happens because that is where solar heating is most intense, driving the most vigorous sublimation. The tail develops as radiation pressure from sunlight pushes the lighter dust particles away from the nucleus, creating the classic comet appearance that has captivated humans for centuries. The dust production rates, estimated from these observations at 10 to 120 kilograms per second, depending on particle size assumptions, fall well within the range seen for active comets in our own solar system. While this may sound like a large amount of material, it is an infinitesimal fraction of the object's total mass. A nucleus just 2 kilometers in radius contains roughly 4 billion kilograms of material, meaning 3i Atlas could maintain its current activity levels for thousands of years without any noticeable depletion. Surface brightness modeling using Hubble data limits the nucleus size to a radius of less than 2.8 kilometers, with some solutions pointing to an object possibly smaller than 1 kilometer across. This size range is perfectly plausible for interstellar debris. Planetary formation processes inevitably create vast amounts of leftover material in these size ranges, and some portion will unavoidably be ejected from their home systems through gravitational interactions with planets or stellar companions. The forward-scattering brightness pattern that has fueled speculation about artificial illumination finds a much simpler explanation in dust physics. When small particles scatter sunlight, the efficiency is highly dependent on the scattering angle, the angle between the incoming sunlight and the direction toward the observer. Forward scattering, where light comes from behind the particles, can be dramatically more efficient than backward scattering for certain particle size distributions. This effect explains why 3i Atlas seems brightest in the sunward direction without needing any exotic energy sources. The dust grains in its coma are simply scattering sunlight more effectively when viewed from particular angles, creating an appearance that might seem unusual to observers unfamiliar with the nuances of optical scattering theory. The orbital dynamics also adhere to natural patterns. The hyperbolic trajectory, with an eccentricity around 6.1, indicates an object moving at typical interstellar velocities. The velocity at infinity of 57 to 58 kilometers per second matches exactly what we would expect for debris that originated in the galactic thick disk and then encountered our solar system's gravitational well. These speeds are not exotic or artificially engineered. They represent the natural outcome of stellar motions within our galaxy. Stars orbit the galactic center at varying speeds depending on their distance and orbital characteristics. When material is ejected from one stellar system and later encounters another, the relative velocities typically fall in the range we observe for 3I Atlas. The near ecliptic alignment, though visually striking, becomes much less mysterious when considered through the lens of observational selection effects. Ground-based sky surveys focus their efforts near the ecliptic plane for practical reasons. That is where most solar system objects are located and where the observing geometry is most advantageous. We are inherently more likely to discover interstellar objects that pass through these well-monitored regions. Additionally, the ecliptic plane is not arbitrary. It represents the gravitational midplane of our solar system, where the combined mass of the Sun and planets creates focusing effects that can preferentially deflect approaching objects toward this plane. The apparent targeting of the ecliptic might actually reflect natural gravitational dynamics rather than intentional navigation. Even the timing of the solar conjunction has a straightforward explanation in orbital mechanics. Any object with a perihelion distance of around 1 to 2 astronomical units will inevitably pass through conjunction as seen from Earth. This is not a designed feature meant to evade observation. It is simply the predictable result of following a hyperbolic orbit with that specific closest approach distance. The sequence of planetary encounters, while superficially appearing like a planned tour, arises from the same orbital geometry that causes the conjunction timing. The retrograde trajectory skimming the ecliptic plane naturally brings 3I Atlas within several astronomical units of multiple planets. But the missed distances are far too large for any meaningful gravitational interactions. These are not targeted flybys. They are simply the unavoidable outcome of tracing a hyperbolic path through a system where most massive objects are concentrated near a single plane. Compositional analysis, though still in its early stages, shows no clear deviations from expected comet chemistry. The difficulty in detecting specific gas species reflects the observational challenges of studying faint emission lines at great distances, not necessarily an unusual chemical makeup. The experience with 2I Borisov reminds us that many spectroscopic signatures only become apparent as objects approach perihelion and heating effects increase gas production to more easily detectable levels. The morphological details revealed by Hubble imaging, the slightly asymmetric dust distribution, the offset between peak brightness and the nuclear center, find ready explanations in the complex physics of cometary outgassing. Real comet nuclei are not perfect spheres with uniform composition. They are rubble piles of ice and rock with irregular surfaces, varying volatile concentrations, and complex internal structures that create localized jets and asymmetric activity patterns. Seasonal effects also have a role. As a comet rotates, different regions of its surface are exposed to varying levels of solar illumination, leading to temporal changes in activity patterns and morphology. Without knowing the rotation period and axis orientation of 3I Atlas, we cannot predict exactly how its appearance should change. But asymmetric and time-variable behavior is the norm rather than the exception for active comets. The statistical argument provides perhaps the strongest natural explanation for the apparent unusualities of 3I Atlas. As our detection capabilities improve and we start observing larger numbers of interstellar objects, we should expect to find some that exhibit characteristics that seem special or unusual simply due to random variation. The Vera Rubin Observatory will potentially discover dozens of interstellar visitors in the coming decade, and basic statistics guarantee that some will have orbital geometries, brightness patterns, or other properties that seem improbable by chance alone. This does not mean unusual objects are necessarily mundane. It means we need to be cautious about inferring intention from apparent improbability. In a large enough sample, even genuinely rare events will happen frequently enough to create false patterns and misleading impressions of design. The accumulating evidence supports a straightforward interpretation. 3I Atlas is an interstellar comet behaving largely as natural physics predicts. Its unusual characteristics reflect the inevitable variations that occur when studying objects from environments we do not fully understand. Viewed through the limitations of our current observational capabilities, the Comet Playbook, refined over centuries of studying objects in our own solar system, seems to work just as well for visitors from other stars. Part 8. When Natural Doesn't Fit, the Gaps and Tensions. The most unsettling mysteries are not the ones where everything appears wrong. They are the ones where almost everything seems right, except for those persistent details that do not quite align. 3I Atlas presents me with exactly this sort of enigma, an object that meets most criteria for natural behavior while consistently producing small inconsistencies that build up into something harder to ignore. Let us examine the gas detection issue. At this stage in 2I Borisov's approach to the Sun, spectroscopic observations were starting to show clear signs of water vapor, carbon monoxide, and other anticipated volatile compounds. These detections were not simple. They demanded careful calibration and advanced analysis techniques, but they provided the chemical fingerprints that definitively identified Borisov as a natural comet. For 3I Atlas, similar spectroscopic searches have yielded frustratingly inconclusive results. Early efforts to detect water vapor, carbon dioxide, carbon monoxide, and cyanide have only produced upper limits, constraints on how much of these gases could be present without being detected, rather than positive identifications of their existence. This does not prove the gases are absent, but it does suggest they are either present at unexpectedly low concentrations or the outgassing is somehow different from typical cometary behavior. The lack of clear gas detections becomes more perplexing when compared to the evident dust activity. Hubble images show significant coma development and dust production rates that necessitate substantial volatile sublimation to lift particles from the nuclear surface. Where is all that gas originating if we cannot detect the expected molecular signatures? One possibility is that 3I Atlas is dominated by more exotic volatiles that do not generate easily detectable spectroscopic lines. Carbon monoxide, for instance, produces weaker emission features than water vapor and might dominate the gas production without being as readily observable. Alternatively, the object might contain significant amounts of very fine dust that scatters light efficiently while requiring less gas production to become airborne. But these explanations begin to feel forced when considered alongside the growing list of other subtle anomalies. The brightness asymmetry offers another instance. While forward scattering can indeed account for enhanced sunward brightness, the degree and persistence of this asymmetry in 3I Atlas stretch the limits of what standard dust models predict for natural particles. Computer simulations of comet dust dynamics typically yield more symmetric coma profiles than what we observe, particularly at the distances where 3I Atlas was first imaged. The sunward concentration seems stronger and more localized than models suggest should happen for randomly distributed particles being pushed by radiation pressure and solar wind effects. Discrepancies in size estimation contribute another layer of complexity. The dramatic revision from early estimates of 10 to 20 kilometers down to just a few kilometers reflects more than simple observational uncertainty. It suggests either the initial assumptions about surface reflectivity were severely incorrect, or the relationship between nucleus size and coma brightness is more complicated than standard models presume. A smaller nucleus generating the observed level of activity implies either unusually high volatile content, the object is more icy than typical comets, or more efficient outgassing mechanisms. Both scenarios are plausible, but would make 3I Atlas statistically unusual compared to the population of comets we have studied in our own solar system. The ecliptic alignment issue persists, despite reasonable explanations involving selection effects and gravitational focusing. While these processes can preferentially guide objects toward the ecliptic plane, quantifying exactly how much bias they introduce requires sophisticated modeling of detection probabilities and interstellar object approach geometries. The existing literature offers rough estimates, but the error bars are large enough that genuinely unusual alignments could still be concealed within the uncertainties. More troubling is the absence of a comprehensive statistical analysis of the complete trajectory geometry. Yes, the ecliptic alignment might be explained by selection effects. Yes, the planetary encounter sequence might be a result of natural orbital mechanics. But what is the probability of both occurring simultaneously, along with the fortuitous solar conjunction timing and the other subtle anomalies we have catalogued? A proper statistical analysis would necessitate careful modeling of observational biases, multiple testing corrections for the number of different anomalies being assessed, and realistic prior probability estimates for various natural and artificial scenarios. Such an analysis is computationally intensive and methodologically challenging, which might be why definitive calculations have not appeared in peer-reviewed literature. The solar conjunction timing warrants particular scrutiny precisely because it is so easily dismissed as natural. While conjunction is indeed common for objects with perihelia around 1 to 2 astronomical units, the timing is remarkably convenient for avoiding detailed observation during peak activity. A truly random arrival time would be just as likely to provide optimal viewing geometry during perihelion passage. The cumulative effect of these gaps and tensions creates what philosophers of science refer to as the problem of auxiliary hypotheses. Each individual anomaly can be explained by adding specific assumptions: unusual dust properties here, atypical volatile composition there, observational selection effects everywhere. But as the number of required auxiliary hypotheses increases, the overall explanation becomes increasingly complex and ad hoc. This does not prove the natural explanation is incorrect, but it does highlight how our confidence in that explanation relies on a growing collection of assumptions that have not been independently confirmed. Science operates best when theories make specific, testable predictions that can be confirmed or refuted through observation. The challenge with 3i Atlas is that most of the proposed natural explanations are flexible enough to accommodate almost any observation after the fact. Rotation period measurements illustrate this problem perfectly. Most active comets show clear periodic variations in brightness and morphology as different surface regions rotate into and out of sunlight. The absence of obvious rotational signatures in 3i Atlas could indicate a very long rotation period, a nearly spherical shape, pole-on viewing geometry, or uniform surface composition. Each explanation is plausible individually, but the lack of independent constraints means we cannot distinguish between them or assess their relative probabilities. The way an object's appearance changes over time offers another domain in which natural models encounter difficulty with exact predictions. The activity of a comet customarily escalates as it nears the Sun, adhering to well-understood connections between its distance from the Sun and the rates of sublimation. However, the specifics are contingent on the nucleus's composition, its thermal characteristics, and its structural properties, which for interstellar objects remain largely undetermined. This ambiguity makes it challenging to differentiate between natural development that just happens to appear strange and genuinely atypical behavior that cannot be accounted for by standard physics. The absence of a significant collection of observations of interstellar comets exacerbates the issue. We have not yet established what constitutes normal for this category of object. What is perhaps most troubling is the possibility of confirmation bias influencing our analysis. Being conditioned by the anomalies of Oumuamua and the continuing discussion regarding potential artificial origins, researchers may be unconsciously more inclined to identify and stress unusual traits while dismissing more conventional explanations. This inclination can manifest in either direction, favoring or disfavoring exotic theories. The focus from the media concerning 3I Atlas generates further pressure for conclusive declarations about its character, even when the scientific investigation remains genuinely unresolved. Press briefings and presentations at conferences have a tendency to highlight the most certain interpretations, which could potentially mask the significant uncertainties that continue to surround crucial observations. I am left with an object that persistently produces minor inconsistencies between what is observed and what is expected. These are not definitive on their own, but taken together, they suggest that our comprehension is still lacking. The central question that 3I Atlas presents to our scientific understanding is whether these knowledge gaps suggest exotic physics or are merely a reflection of the constraints of observing unfamiliar objects with less than perfect instruments. Part 9. The concept of intention. What would it signify for a path to be chosen? Imagine being a cosmic traffic controller, monitoring objects as they journey through three-dimensional space at incredible velocities across expanses that dwarf human comprehension. What would it even signify for one of those paths to be selected, rather than being the unavoidable outcome of gravitational laws and arbitrary starting conditions? This inquiry goes to the core of what I am truly asking when I contemplate whether the path of 3I Atlas exhibits indications of purpose. On the most fundamental level, a chosen path would necessitate some kind of active steering, the capacity to execute course alterations that diverge from a path dictated solely by gravity. In my own solar system, spacecraft exhibit this kind of capability by using rocket engines to modify their velocity in specific directions at particular moments. These actions leave behind noticeable traces in the form of abrupt changes in acceleration that cannot be attributed to gravitational forces alone. Oumuamua served as a perfect illustration of how faint such traces can be. Its non-gravitational acceleration was a mere 17 meters per second in total, just enough to alter the object's velocity by the speed of a slow jog over its entire transit through the inner solar system. Nevertheless, this minute divergence was detectable because astronomers were able to monitor the object's location with exceptional accuracy over a period of several months. To detect comparable acceleration signatures for 3I Atlas would demand astrometric monitoring of equal precision. The object's location must be measured repeatedly over long durations, with uncertainties small enough to discern velocity shifts of meters per second against a backdrop of movement at tens of kilometers per second. It is akin to attempting to determine if a person walking across a football field has subtly changed their gait by examining pictures captured from an aircraft. At present, observations reveal no signs of such trajectory alterations. 3I Atlas seems to trace a purely gravitational hyperbola, with its projected future locations aligning with observations within the bounds of measurement errors. However, these errors are still considerable enough that minor course adjustments could be concealed within the observational noise. A more advanced method of guidance could entail ballistic targeting, calculating a path that accomplishes particular objectives without the need for mid-course adjustments. This strategy would be significantly harder to identify because the object would trace a natural gravitational course that just so happens to create optimal observation angles or a favorable sequence of encounters. Such targeting would demand extraordinary computational accuracy and sophisticated foresight. The trajectory would need to be computed not only to arrive at our solar system, but to do so with the precise velocity and direction needed to fulfill whatever goals the guidance system had in mind. The room for error would be incredibly slim. Minor inaccuracies in the initial conditions would be magnified over interstellar distances, resulting in massive errors in position. And yet, if such accuracy were possible, the resulting trajectory could be nearly impossible to distinguish from a natural one. The only indications would be statistical, the unlikelihood that random occurrences would yield such seemingly deliberate geometry. This leads me directly into the domain of probability theory and the difficulty of separating design from chance. What particular goals might warrant such a complex navigational plan? Reconnaissance stands out as the most apparent potential objective. An advanced civilization might wish to examine habitable planets, technological indicators, or the general features of other star systems without disclosing their presence. A journey through the inner solar system would present chances to study Earth, Mars, Venus, and possibly find artificial constructions or electromagnetic signals that point to a technological civilization. However, the geometry of the encounters of 3I Atlas appears to be poorly suited for thorough reconnaissance. The nearest it comes to Earth is at 1.88 astronomical units, which is roughly 270 million kilometers, a distance far too great for high-resolution photography of surface details or man-made structures. Even my most sophisticated space telescopes find it difficult to discern planetary features at such distances. More unusual goals could include the deployment of instruments, such as leaving behind small monitoring probes during planetary encounters that could stay in the system for long-term observation. Such probes would have to be incredibly small to go unnoticed, and their release would probably generate noticeable signs like changes in trajectory or trails of debris. Another speculative idea is that it could serve as a communication relay. An interstellar object might function as a carrier of data, gathering information as it passes through the solar system, and then sending it to receivers in its home system or elsewhere. This would necessitate advanced communication systems and power supplies that could be identified by their electromagnetic signals or heat signatures. The timing of the solar conjunction introduces another layer to scenarios based on intent. If 3I Atlas was engineered to evade close examination during its most dynamic period, placing itself behind the Sun during its passage at perihelion would be a clever tactic. On the other hand, the conjunction could offer the perfect timing for actions that require minimal observation from Earth, such as deploying instruments, making course corrections, or communicating with other assets in the system. However, these scenarios compel me to make many assumptions about the abilities and goals of hypothetical alien civilizations. I am essentially trying to deduce intent from observed actions, which is a notoriously unreliable method even when analyzing human behavior, let alone the creations of entirely foreign minds working with unimaginable limitations. The task gets even more complicated when I entertain the notion of distributed reconnaissance. Instead of dispatching a single complex probe, an advanced civilization might send out a great number of simpler objects made to resemble natural debris but equipped with minimal sensor arrays. Such a tactic would be much more difficult to spot and could allow for the comprehensive surveillance of many star systems at once. Current SETI protocols are mainly centered on radio and optical signals, attempting to find deliberate communications or the electromagnetic markers of advanced technology. But passive reconnaissance objects might not emit any detectable signals at all, looking just like natural debris except for slight trajectory deviations or statistical trends that become apparent only when a large number of objects are studied together. This brings up deep questions about the definition of evidence and the level of proof I should demand for claims of artificial origin. How unlikely must a trajectory be before I start to seriously entertain non-natural causes? How many seemingly strange characteristics need to accumulate before chance becomes a less believable explanation than design? The philosophical ramifications go beyond the particular instance of 3I Atlas. If I am being observed by advanced civilizations using disguised probes, my ability to detect such surveillance might rely as much on my conceptual models and analytical techniques as on my technological prowess. I could be surrounded by artificial objects that I consistently label as natural because my beliefs about what artificial objects ought to look like are fundamentally flawed. Conversely, my pattern-detecting mind might be producing false positives, seeing artificiality in natural phenomena because I am predisposed to search for signs of intelligence in ambiguous information. The annals of science are filled with instances of phenomena that were initially mysterious, but were eventually explained by conventional science as observational tools improved and theoretical knowledge grew. The question of intent ultimately compels me to face the boundaries of the scientific method when confronted with potentially intelligent phenomena. Science is excellent at testing hypotheses against observations, but intelligence is specifically designed to thwart such analysis by imitating natural processes and evading detection. I may require entirely new methods to differentiate between sophisticated camouflage and authentic natural behavior. For the moment, 3I Atlas proceeds on its meticulously orchestrated path through my solar system, tracing a course that could represent either the beautiful determinism of celestial mechanics or the deliberate purpose of minds I cannot begin to fathom. The difference may be less important than my readiness to stay open to both interpretations while upholding the strict standards of evidence that separate science from mere speculation. Part 10. Cosmic Scales of Chance. How improbable is this trajectory? Imagine a cosmic gambling house where the dice possess billions of sides and the roulette wheel turns through dimensions I can hardly conceive. Every path through space is a single result from a nearly endless set of possibilities. Yet my brain, which evolved to identify patterns on the African savanna, insists on perceiving deliberate design in what could be nothing more than the unavoidable consequence of rolling cosmic dice a sufficient number of times. This represents the core difficulty in determining whether the trajectory of 3 Atlas is a true anomaly or simply a matter of statistical inevitability. When I am dealing with the astronomical scales of space, time, and probability, my intuitive sense of what is improbable completely fails me. Let's first examine the fundamental geometry. The ecliptic plane, that unseen disk where my planet orbits, constitutes a minuscule portion of all conceivable approach angles for an interstellar object. Imagine a sphere enveloping my solar system. The ecliptic plane intersects this sphere like a razor-thin cut through an orange. The likelihood that a randomly aimed trajectory would align within 5 degrees of this plane seems incredibly low. However, this calculation overlooks critical observational biases that tilt my sample precisely toward such trajectories. Ground-based sky surveys focus their work near the ecliptic for entirely sensible reasons. This is where the majority of asteroids and comets are located, where the atmosphere causes the least interference, and where the viewing conditions are most advantageous. I might find 50 objects near the ecliptic for every one I locate at a high inclination, simply because I am not searching as diligently in other directions. The matter gets even more intricate when I take into account the effects of gravitational focusing. My solar system is not merely empty space with a star and planets randomly distributed within it. It is a gravitational framework that actively shapes the paths of objects approaching it. Computer models indicate that the collective gravitational pull of the Sun and planets can steer interstellar objects preferentially toward the ecliptic plane, especially if they arrive with the relatively slow speeds characteristic of the thick disk stellar populations. To measure these effects requires complex modeling that considers the distribution of stellar velocities in my galactic vicinity, the gravitational layout of the solar system, and the observational capacities and search methods of current sky surveys. Such computations are demanding and heavily reliant on assumptions about variables that are not known with certainty. The limited published estimates indicate that ecliptic alignments could be several times more probable than simple geometric reasoning would suggest, but the uncertainties are significant enough that truly rare events might still be concealed within the margins of error. I am essentially attempting to differentiate between unlikely and very unlikely using statistical methods that were not created for such extreme situations. The sequence of planetary encounters introduces another level of seeming improbability. What are the chances that a random path would result in close flybys of Mars, Venus, Earth, and Jupiter in a tidy chronological order? Once more, a straightforward calculation points to astronomical odds against such an event. However, close approaches is a subjective term that requires precise definition. The actual missed distances of 0.19 astronomical units for Mars, 0.6565 for Venus, 1.8 for Earth, and 0.36 for Jupiter are substantial by the standards of spacecraft missions. These are not exact flybys meant to harness gravitational energy or meet specific targeting goals. They are merely the unavoidable result of a retrograde hyperbolic trajectory passing through a system where most of the massive bodies are concentrated near a single plane. The key realization is that any trajectory that grazes the ecliptic plane will invariably pass by multiple planets at different distances. The particular order and timing are determined by the precise orbital geometry, but some form of multi-planet encounter sequence is almost certain rather than improbable. I am not figuring out the odds of hitting particular targets, but rather the likelihood that targets are situated along a predetermined route. The timing of the solar conjunction offers another instance of apparent fine-tuning that unravels upon closer examination. The fact that 3I Atlas vanishes behind the Sun during its nearest approach seems suspiciously convenient for an object seeking to evade detailed scrutiny. But any object with a perihelion distance of about 1 to 2 astronomical units will inevitably undergo conjunction as seen from Earth. It is a geometric requirement, not an engineered characteristic. The timing is not even especially unusual. Objects with comparable perihelion distances include many asteroids and comets that frequently experience conjunction during their closest approaches to the Sun. If I were to survey all such objects over time, I would find that conjunction during perihelion passage is the standard rather than the exception. Yet my mind resists these statistical arguments because they clash with deeply rooted intuitions about intention and design. When I observe a sequence of events that seems to have a purpose, I instinctively conclude that a purpose is present. This cognitive bias was beneficial for my ancestors when they interpreted animal behavior or social interactions, but it becomes a hindrance when analyzing cosmic phenomena that occur on scales far beyond human experience. The birthday paradox serves as a helpful analogy for comprehending how seemingly improbable events can be statistically unavoidable. In a group of just 23 people, there is a more than 50% probability that 2 will have the same birthday. This outcome appears counterintuitive until one grasps that they are not calculating the probability of a specific match, but rather the likelihood that any match exists among all possible pairings. Likewise, as I enhance my detection capabilities and start to observe a greater number of interstellar objects, I should anticipate that some will exhibit traits that seem improbable by chance alone. The Vera Rubin Observatory is set to discover dozens of such objects in the next decade, and fundamental statistics ensure that several will possess orbital geometries, timing coincidences, or other features that appear intentionally orchestrated. This does not imply that unusual objects are necessarily ordinary. It means I must be exceptionally cautious about deducing design from apparent improbability. The calculation must consider not only the specific sequence of traits I observe, but also the selection effects that draw my attention to certain types of objects, while I completely miss others. Publication bias exacerbates these statistical difficulties. Research articles and media reports naturally emphasize the most captivating and unusual findings, leading to a systematic skew in my perception of how frequently various phenomena actually occur. I hear about objects with extraordinary trajectories precisely because they are extraordinary, not because they are typical of the general population. Multiple testing corrections are another vital consideration that is often ignored in sensational reports about improbable trajectories. When I scrutinize any complex object for unusual features, I am essentially conducting dozens or hundreds of different statistical tests: orbital geometry, brightness fluctuations, spectroscopic signatures, temporal evolution, and so on. The probability that at least one of these tests will produce a seemingly significant result by chance alone can be quite high, even if no genuine anomalies are present. A proper statistical analysis would necessitate pre-registering my hypotheses, defining in advance exactly which characteristics I deem anomalous and what probability thresholds I will use to separate unusual from normal behavior. Post hoc analysis, where I define unusual based on what I actually see, is susceptible to cherry-picking effects that can make even entirely random data seem significant. The velocity distribution of interstellar objects offers another check on claims of artificial targeting. 3I Atlas is moving at 57 to 58 kilometers per second relative to the local standard of rest, which is precisely the speed I would expect for debris from the galactic thick disk population. Higher velocities might indicate artificial propulsion, while lower speeds could suggest objects that were intentionally slowed down for capture. The observed velocity is perfectly ordinary. Even the most advanced targeting system would be constrained by the fundamental principles of orbital mechanics and energy demands. To achieve a specific trajectory requires not just precise navigation, but also immense energy expenditures to counteract the natural inclination of objects to follow gravitational paths. The more precisely targeted the trajectory, the more energy is needed to maintain that precision against perturbations and uncertainties. These energy demands increase dramatically with the level of precision required. Attaining the milli-arc-second positional accuracy needed for genuinely targeted planetary encounters would necessitate propulsion systems far beyond anything in my technological arsenal, and such systems would likely leave detectable traces in the form of exhaust trails, thermal radiation, or electromagnetic disturbances. The lack of any such traces does not definitively exclude artificial guidance. Advanced civilizations might have propulsion technologies that operate on physical principles I do not yet understand. But it does imply that if artificial guidance is at play, it operates at such a subtle level that distinguishing it from natural gravitational movement relies on statistical arguments rather than direct physical proof. Perhaps most crucially, I lack the baseline data required to determine what constitutes genuinely unusual behavior for interstellar objects. My sample is composed of exactly 3 confirmed detections, which is hardly enough to establish normal ranges for orbital characteristics, activity levels, or encounter geometries. What appears anomalous for 3I Atlas might turn out to be completely typical once I have observed dozens or hundreds of similar objects. The growing sample size will eventually furnish the statistical power needed to differentiate between natural variation and genuinely anomalous behavior. But until that larger dataset is available, claims about the improbability of specific trajectories remain highly speculative, contingent on assumptions about selection effects, detection biases, and population characteristics that I cannot yet confirm. In the interim, 3I Atlas continues its meticulously orchestrated path through my solar system, tracing a course that could represent either cosmic coincidence or deliberate purpose. The distinction may be less important than my recognition that in a universe vast enough to contain billions of star systems and trillions of potential interstellar wanderers, even the most improbable events become inevitable given sufficient time and opportunity. Part 11. The Alien Probe Hypothesis. Why it will not disappear. There is an almost magnetic allure to the idea that I am not alone in the universe, and that magnetism becomes overwhelming when I am confronted with objects that defy easy categorization into my established norms of behavior. Oumuamua unlocked this particular Pandora's box in 2017, and 3 Atlas has ensured it stays defiantly ajar, no matter how many conventional explanations I try to stack on top of it. The enduring nature of the alien probe hypothesis is not merely about the public's fascination with extraterrestrial life, although that is certainly a factor. It mirrors a real tension within the scientific community regarding how to strike a balance between healthy skepticism and an openness to extraordinary possibilities. This tension became clear with Oumuamua and now applies to every subsequent interstellar visitor. Harvard's Avi Loeb has emerged as the most notable proponent of keeping artificial explanations under consideration. His argument for Oumuamua being potentially artificial, based on its strange acceleration and absence of visible outgassing, ignited a fierce debate that persists to this day. When 3I Atlas emerged with its own set of subtle anomalies, Loeb and his colleagues promptly applied their analysis to this new arrival. Their method is interesting from a procedural standpoint. Instead of making a definitive claim of artificial origin, they advocate for considering multiple hypotheses until conclusive evidence is found. They highlight the ecliptic alignment of 3 Atlas, its sequence of planetary encounters, and its brightness characteristics as features that merit close examination rather than prompt dismissal. The objective is not to prove an alien visit, but to avoid the premature termination of scientific investigation. This stance has elicited strong criticism from other astronomers who contend that extraordinary claims demand extraordinary evidence and that the current observations of 3 Atlas are well within the spectrum of natural comet behavior. The Hubble Space Telescope analysis, which revealed clear outgassing activity and dust production, has been particularly persuasive in steering scientific consensus toward conventional explanations. However, the debate exposes deeper philosophical disparities concerning the nature of scientific conservatism. Critics assert that considering alien probe hypotheses without convincing evidence damages scientific credibility and fuels public conspiracy theories. Supporters argue that excessive caution could lead to missing truly revolutionary discoveries and that the potential consequences of contact with extraterrestrial intelligence warrant a more proactive investigation of anomalous objects. The media dynamics surrounding these discussions introduce their own set of complications. News organizations are naturally drawn to the "could it be aliens?" narrative because it drives clicks and audience engagement. Scientific articles describing normal comet behavior seldom make the news, whereas speculative blog posts about artificial objects can become viral in a matter of hours. This imbalance in media coverage can create misleading impressions about the state of scientific agreement. Academic journals are subject to similar pressures. Papers that propose exotic explanations for astronomical phenomena tend to receive more citations and media attention than those that confirm conventional interpretations. Although peer review offers some measure of quality control, the publication system still favors novelty and controversy over the careful validation of mundane explanations. Professional astronomers must handle these pressures while upholding their scientific integrity. Many admit in private that the current observations of 3 Atlas could support various interpretations, but they are hesitant to express this uncertainty in public for fear of fostering premature conclusions or conspiracy theories. This often leads to an artificially polarized public discourse that fails to capture the genuine subtleties of scientific opinion. The Galileo project, initiated partly in reaction to the Oumuamua controversy, seeks to tackle these issues through systematic search methods specifically created to find technological artifacts in near-Earth space. Instead of debating the interpretation of ambiguous objects after their discovery, the project intends to use instrumentation designed to differentiate between natural and artificial phenomena. This strategy recognizes that my current astronomical infrastructure, which is primarily built for studying natural phenomena, may not be ideal for identifying subtle indications of technology. Artificial objects might have different infrared signatures than natural bodies, possess structural features that are only visible at high resolution, or show trajectory changes too small to be detected by standard astrometric methods. The concept of astroarchaeology expands on this idea to include methodical searches for technological artifacts throughout the solar system. Just as terrestrial archaeology examines ancient human civilizations through their physical artifacts, Astroarchaeology would seek evidence of past visits by studying objects in unusual orbits with anomalous compositions or with suspicious geometries. This approach rephrases the question from "Is 3I Atlas artificial?" to "How would I systematically distinguish between natural and artificial objects among the wider population of interstellar visitors?" The distinction is significant because individual objects will always be open to multiple interpretations, but population-level statistics might uncover patterns that definitively point to either natural or artificial origins. The difficulty is in creating testable predictions that can differentiate between these scenarios. Natural interstellar objects should conform to statistical distributions for size, composition, activity level, and trajectory that are consistent with the physics of planetary system formation and stellar dynamics. Artificial objects might exhibit different patterns, perhaps size distributions centered on particular values, unusually consistent compositions, or trajectory geometries tailored for specific observational purposes. However, these population-level indicators will only become evident as my sample size increases from the current 3 confirmed interstellar objects to dozens or hundreds. The Vera Rubin Observatory is poised to greatly accelerate this process, potentially offering the statistical power required to distinguish between competing hypotheses about the nature and origin of interstellar visitors. Individual case studies like 3 Atlas are still valuable, even if they cannot definitively settle the artificial versus natural debate. Each object provides an opportunity to develop analytical techniques, improve observational strategies, and fine-tune my ability to derive information from sparse datasets. These abilities will be essential as the rate of detection grows, and I am compelled to make swift judgments about potentially significant discoveries. The ethical aspects of this research also merit consideration. If I am being observed by advanced civilizations, my reaction to that discovery could have profound consequences for the future of humanity. The premature release of ambiguous evidence might cause panic or false optimism, while excessive secrecy could erode public confidence in scientific institutions. The SETI community has established protocols for managing the potential detection of extraterrestrial intelligence, but these are mainly focused on radio and optical signals rather than physical artifacts. The discovery of confirmed technological objects in my solar system would necessitate new frameworks for verification, communication, and response that are not currently in place. Public education is vital in this context. The general populace needs to comprehend both the legitimate scientific questions posed by objects like 3 Atlas and the strict standards of evidence needed before arriving at extraordinary conclusions. Science communication that either disregards interesting possibilities or exaggerates preliminary findings can harm public trust and scientific credibility. The persistence of the alien probe hypothesis ultimately mirrors humanity's profound desire to comprehend my place in the universe. Am I alone, or am I part of a larger community of intelligent beings? Do I reside in a cosmos where intelligence is so uncommon that I may never encounter it, or one where advanced civilizations regularly explore other star systems? These inquiries go beyond the specific instance of 3 Atlas or any single object. They touch upon fundamental issues concerning the nature of intelligence, the probability of technological civilization, and the chance that my seeming isolation might be an illusion upheld by species far more advanced than my own. Whether 3 Atlas is a piece of natural debris from another star system or something more remarkable, it acts as a mirror reflecting my hopes, fears, and beliefs about intelligence in the universe. The trajectory may or may not have been chosen, but my reaction to that possibility says something profound about the kind of species I am becoming as I take my initial, tentative steps toward understanding my place in the galactic community. As 3 Atlas continues its course toward perihelion and beyond, the alien probe hypothesis will likely endure, not because the evidence necessitates it, but because the question it embodies touches upon something fundamental to human curiosity and my connection with the cosmos that envelops me. Part 12. A trajectory toward Earth, or simply through the inner system? Nothing fuels speculation quite like a misunderstood trajectory. And few things are more commonly misunderstood than the three-dimensional geometry of orbital motion. When news outlets first reported that 3I Atlas would approach Earth, the headlines conjured images of a cosmic visitor making a beeline for my planet. The reality is simultaneously more mundane and more fascinating. This interstellar wanderer will thread through my solar system's inner regions like a needle through fabric, coming nowhere near my world while providing a masterclass in celestial mechanics. Let me map out the actual itinerary. On October 3, 2025, 3I Atlas sweeps past Mars at 0.19 astronomical units, approximately 19 million miles. To put this in perspective, that is about 50 times the distance from Earth to the Moon and nearly 20 times closer than Mars ever comes to Earth during its closest approaches. Not exactly a collision course, but close enough to wave hello if anyone happened to be watching from Martian orbit. The journey continues with 3 Atlas rounding the Sun at perihelion on October 29th to 30th at approximately 1.36 to 1.44 astronomical units, just inside the average orbital distance of Mars. This closest approach to my star represents the gravitational climax of the object's solar system visit, where it will experience maximum heating and potentially maximum activity as subsurface ices sublimate under intense solar radiation. On November 3rd comes the Venus encounter at 0.6565 astronomical units, about 60 million miles from the cloud-shrouded planet. Once again, this represents a reasonably close passage by solar system standards, but far too distant for any meaningful gravitational interaction or detailed observation of either body by the other. Then comes the encounter that generates the most media attention, Earth's closest approach on December 19th at 1.8 astronomical units. This distance, roughly 270 million kilometers, places 3I Atlas about twice as far from Earth as Mars is during its closest approaches to my planet. To casual observers reading news headlines, approaching Earth might sound ominous, but astronomically speaking, it is a distant flyby that poses absolutely no threat. Finally, the grand tour concludes with a Jupiter encounter on March 16th, 2026 at 0.36 astronomical units, about 34 million miles from the giant planet. This represents the closest approach to any planet during the entire solar system passage. Yet, it is still more than 80 times the distance from Earth to the Moon. NASA and the European Space Agency have repeatedly emphasized that 3I Atlas poses no threat to Earth whatsoever. The closest approach distance of 1.8 astronomical units provides an enormous safety margin. Even if my orbital calculations were off by millions of miles, there would still be no possibility of collision. Yet the persistent media focus on Earth approach distances reveals how easily astronomical geometry can be misinterpreted by audiences unaccustomed to thinking in 3 dimensions across vast scales. The trajectory appears carefully planned only when viewed through the lens of human spatial intuition. I see a sequence of planetary encounters and imagine intentional targeting, like a tourist planning visits to multiple cities during a European vacation. But orbital mechanics operates under different rules than highway travel or airline schedules. 3I Atlas follows a single continuous hyperbolic path that was determined by its velocity and direction when it entered the solar system's gravitational influence. The sequence of planetary encounters results from the simple fact that most planets orbit relatively close to the ecliptic plane, and any trajectory skimming that plane will necessarily pass near multiple worlds. The specific distances and timing depend on exactly when and where the planets happen to be positioned during the object's passage, not on any navigation system attempting to optimize viewing geometry. This distinction becomes crucial when evaluating claims about purposeful reconnaissance or surveillance. A genuine probe designed to study my solar system would likely prioritize much closer approaches to planets of interest, particularly Earth. The actual encounter distances are too large for detailed surface observations or detection of technological signatures that might indicate intelligent life. Even my most advanced space telescopes struggle to resolve planetary surface features at the distances involved in 3I Atlas's encounters. The Hubble Space Telescope can just barely make out the largest features on Mars when that planet is at its closest approach to Earth, about 100 times closer than 3I Atlas will pass. Detecting signs of civilization or even life would require proximity measured in thousands of miles, not millions. The apparent tour of the inner solar system becomes even less impressive when I consider that 3I Atlas will actually be poorly positioned to observe most of these worlds during its closest approaches. The geometry of its retrograde orbit means the object will be viewing the night sides of planets during many encounters or approaching from angles that provide limited surface visibility. More importantly, if 3I Atlas were designed for reconnaissance, why limit itself to passive observation from such enormous distances? An advanced civilization capable of interstellar travel would presumably have technologies that could achieve much closer approaches, deploy smaller observation satellites, or establish longer-term monitoring capabilities within the solar system. The trajectory's most suspicious characteristic might actually be its lack of optimization for any obvious reconnaissance objectives. It is almost as if someone took a genuine interstellar comet trajectory and then complained that it was not following the path a properly designed spy probe would choose. Solar conjunction timing adds another layer to the trajectory analysis. As 3I Atlas reaches its closest approach to the Sun, it will be positioned almost directly behind my star as viewed from Earth, making detailed observations extremely difficult during what should be its most active and interesting phase. Some have interpreted this timing as evidence of deliberate concealment, an attempt to avoid scrutiny during peak activity. But astronomical geometry does not respect my observational preferences. Any object with a perihelion distance around 1 to 2 astronomical units will inevitably experience conjunction as viewed from Earth. The timing is not chosen, it is an unavoidable consequence of orbital mechanics. Hundreds of asteroids and comets regularly pass through similar conjunctions without anyone suggesting they are trying to hide from human observation. The conjunction actually represents a missed opportunity if 3I Atlas were designed for reconnaissance. The period around perihelion, when the object is most active and potentially most observable, coincides with the worst possible geometry for Earth-based telescopes. A competent surveillance mission would arrange its trajectory to maximize observability during peak activity, not minimize it. Professional observatories are adapting their strategies to work around the conjunction limitations. Space-based telescopes like Hubble can observe closer to the Sun than ground-based instruments, though even they have limits on how close to my star they can point safely. Solar observatories designed to study the Sun itself might be able to track 3 Atlas during conjunction, though separating the object from the overwhelming glare of my star would be extremely challenging. The post-conjunction observations scheduled for early December 2025 will be crucial for understanding how the object has been affected by its close solar encounter. Many comets show dramatic changes in activity level, morphology, and even structural integrity after perihelion passage. Some fragment under thermal stress, while others develop enhanced outgassing that makes spectroscopic analysis much more productive. If 3I Atlas were artificial, these post-perihelion observations might reveal characteristics that distinguish it from natural comets. Artificial objects should be more resistant to thermal damage and might display activity patterns inconsistent with sublimating ice. Natural comets often become more active after perihelion as subsurface layers are exposed and volatiles previously protected by overlying material begin to outgas. The trajectory ultimately tells a story of gravitational inevitability rather than intentional navigation. 3I Atlas entered my solar system with a specific velocity and direction that determined its entire subsequent path. The planetary encounters, conjunction timing, and Earth approach distance are all consequences of that initial trajectory, modified only by the predictable gravitational influences of the Sun and planets. Whether that initial trajectory was itself chosen remains an open question, but the solar system passage appears to be simply the natural result of following gravitational physics from point A to point B across interplanetary distances. Not a grand tour, not a reconnaissance mission, but simply a visitor passing through my cosmic neighborhood on its way to somewhere else entirely. Part 13. Testing Humanity, a Speculative Lens. What if 3I Atlas is not primarily about studying my solar system at all, but about studying me? This thought experiment pushes me into the realm of pure speculation, but it is speculation with a purpose, exploring how my response to anomalous objects might itself be the phenomenon being observed. If an advanced civilization wanted to understand how emerging technological species react to potential contact scenarios, they might design tests that reveal as much about the observers as the observed. The concept resembles psychological experiments where the stated purpose masks the real objective. Researchers might claim they are testing memory or decision-making while actually measuring social conformity or ethical reasoning. Similarly, an interstellar object that appears to be passing through my system for natural reasons might actually be designed to provoke specific responses that reveal my scientific maturity, coordination capabilities, and readiness for broader galactic contact. Consider what 3I Atlas has already accomplished in terms of testing human systems. Within hours of its discovery, observatories across 6 continents were coordinating observations through the Minor Planet Center. Professional and amateur astronomers collaborated to track its motion and brightness. Space agencies issued measured public statements, balancing scientific excitement with appropriate caution. Social media exploded with speculation ranging from thoughtful analysis to wild conspiracy theories. This global response pattern would provide valuable intelligence about my species' current capabilities and social structures. How quickly can I coordinate international scientific collaboration? How effectively can I distinguish between evidence-based analysis and unfounded speculation? How do my media systems handle potentially extraordinary discoveries? These questions might be far more interesting to an advanced civilization than anything they could learn from distant observations of my planets. The trajectory's timing seems almost optimized to test these systems. The discovery months before perihelion provided enough lead time for extended observation campaigns, but not so much that public interest would wane. The solar conjunction creates a natural break in observations that tests my patience and ability to maintain scientific programs across gaps in data collection. The post-conjunction reappearance offers opportunities to assess how well my predictions matched reality. Even more intriguingly, the object's characteristics seem calibrated to generate exactly the kind of debate I am currently experiencing. Too obviously artificial, and I might panic or withdraw from space exploration entirely. Too obviously natural, and I might dismiss it without learning anything about my own analytical capabilities. Instead, 3I Atlas presents me with a puzzle that is genuinely ambiguous, natural enough to prevent panic, unusual enough to command attention. The ecliptic alignment provides a perfect example. It is unusual enough to spark speculation about artificial guidance, but not so unprecedented that it could not result from natural selection effects and gravitational focusing. This ambiguity forces me to confront the limits of my statistical analysis, my understanding of observational biases, and my ability to distinguish between coincidence and design. The planetary encounter sequence offers another test of my interpretive frameworks. Do I see a random trajectory that happens to pass near multiple worlds or a carefully planned reconnaissance mission? My answer reveals something fundamental about my tendency to project intentionality onto ambiguous phenomena, a cognitive trait that might be crucial for understanding how I would respond to more obvious signs of extraterrestrial intelligence. The media response patterns would be particularly informative to external observers. Within days of the discovery announcement, I generated thousands of articles, blog posts, social media discussions, and video analyses covering every conceivable interpretation from mundane comet to alien mothership. This explosion of commentary would provide a comprehensive sample of human reasoning processes, cultural biases, and communication strategies. When faced with potentially extraordinary phenomena, scientific institutions revealed their own characteristics through their responses. NASA and ESA issued careful, measured statements emphasizing safety and scientific opportunity while avoiding speculation about exotic origins. Professional astronomers generally favored natural explanations while acknowledging remaining uncertainties. The peer review process slowly ground through its deliberate methodology of hypothesis, testing, and evidence evaluation. These institutional responses would tell external observers important things about my decision-making processes, risk management strategies, and cultural values. How do I balance scientific caution against public curiosity? How effectively can my institutions manage information flow during potentially revolutionary discoveries? How do I handle disagreement among experts when stakes are high and evidence is ambiguous? The timing of conjunction could represent a particularly sophisticated test element. By disappearing behind the sun during its most active phase, 3I Atlas creates a natural experiment in delayed gratification and scientific patience. Do I maintain rigorous observation programs even when immediate results are not available? How well do I predict what I will find when observations resume? Can I resist filling observational gaps with unfounded speculation? More subtly, the conjunction timing tests my technological capabilities and international cooperation. Space-based telescopes can observe closer to the sun than ground-based instruments, but coordination between different observatory systems requires sophisticated communication and data-sharing protocols. Successfully tracking an object through conjunction demands exactly the kind of technological and institutional capabilities that would be prerequisites for broader space exploration and eventual interstellar communication. The size estimation confusion, from early reports of a massive 20-kilometer object down to current constraints of just a few kilometers, would reveal important information about my measurement capabilities and error correction processes. How quickly can I recognize and correct systematic errors in my analysis? How effectively do I communicate uncertainty to both scientific and public audiences? Do I learn from mistakes or repeat similar errors with subsequent discoveries? Even my speculation about artificial origins serves as a kind of inadvertent self-revelation. The fact that I seriously consider whether interstellar objects might be probes demonstrates both my awareness that I am not necessarily alone in the universe and my assumption that other intelligences would be interested in studying me. These attitudes would tell external observers significant things about my level of cosmic consciousness and my readiness for contact scenarios. The international coordination aspects of my response would be particularly revealing. Despite political tensions and competing national interests, the astronomical community has maintained remarkable cooperation in tracking and studying 3I Atlas. This suggests that my species might be capable of unified responses to cosmic phenomena even when I struggle with coordination on purely terrestrial issues. My technological capabilities would also be on full display. The rapid trajectory calculations, spectroscopic analysis attempts, and sophisticated imaging through Hubble demonstrate that I have achieved significant technical competence in astronomical observation and analysis. But the limitations of my capabilities, the ambiguous gas detections, uncertain size estimates, and incomplete characterization would also be apparent to any observers with superior technology. Perhaps most importantly, my handling of uncertainty itself becomes a key indicator of intellectual maturity. Science advances through careful hypothesis testing and gradual accumulation of evidence, but public discourse often demands immediate, definitive answers. How well I navigate this tension, maintaining appropriate scientific skepticism while remaining open to extraordinary possibilities, might serve as a crucial indicator of my readiness for cosmic citizenship. If this speculative framework has any validity, then 3I Atlas represents less a test of my ability to detect alien technology than a test of my capacity to think clearly about ambiguous phenomena under intense scrutiny. The object might be entirely natural, but my response to it reveals authentic characteristics of my civilization that no amount of passive observation could uncover. Whether designed as a test or not, 3I Atlas certainly functions as one, challenging my scientific methods, institutional coordination, media systems, and public reasoning capabilities in ways that reveal fundamental features of human civilization at its current level of development. In that sense, every interstellar visitor serves as a mirror, reflecting my own cosmic coming-of-age back to me across the vast scales of space and time. The test continues as 3I Atlas approaches perihelion and beyond. How I handle the remaining unknowns may matter more than what I ultimately discover about the object itself. Part 14. The limits of what I know, data, gaps, and next steps. Science is fundamentally a conversation between what I think I know and what the universe actually reveals when I look closely enough. For 3I Atlas, that conversation has been enlightening, frustrating, and occasionally contradictory. A perfect example of how the most interesting discoveries emerge from the spaces between certainty and ignorance. Let me start with what I can say with confidence. The astrometric data, precise measurements of the object's position over time, provide rock-solid evidence for its interstellar origin and hyperbolic trajectory. Multiple observatories worldwide have tracked 3I Atlas across several months, building an observational arc that nails down its orbital characteristics with high precision. The eccentricity of approximately 6.1, the inclination of 175 degrees, and the sequence of planetary encounters are as well established as orbital mechanics allows. The Hubble Space Telescope observations represent another pillar of reliable data. These images clearly show a developed coma, evidence of sunward dust emission, and a faint anti-solar tail, the hallmarks of an active comet. The surface brightness modeling constrains the nucleus size to a radius of less than 2.8 kilometers, possibly much smaller. The dust production rates of 10 to 120 kilograms per second fall within reasonable ranges for cometary activity at several astronomical units from the Sun. Photometric measurements from multiple facilities provide consistent evidence for gradual brightening as the object approaches perihelion, following patterns broadly similar to other comets at comparable distances. The color measurements, while still preliminary, suggest properties not dramatically different from typical cometary dust, though with some potential variations that require additional observations to confirm. But these islands of solid knowledge are surrounded by oceans of uncertainty that reveal just how much I still do not understand about 3I Atlas and interstellar objects in general. The spectroscopic data remains tantalizingly incomplete. Despite dedicated observing campaigns at multiple facilities, attempts to detect specific gas species, water vapor, carbon monoxide, carbon dioxide, cyanide, have yielded only upper limits rather than clear detections. This does not necessarily indicate unusual chemistry. Faint emission lines are notoriously difficult to detect against the background sky, particularly for distant objects with modest activity levels. The experience with 2I Borisov provides both hope and caution here. That object's most distinctive spectroscopic signatures only became apparent as it approached perihelion, and heating effects boosted gas production to more easily detectable levels. 3I Atlas may yet reveal its chemical fingerprints as solar heating intensifies, but I will not know until the observations are completed and analyzed. Detailed morphological analysis remains limited by the fundamental challenges of distinguishing nucleus properties from coma contamination. While Hubble's sharp vision can separate these components better than ground-based telescopes, the modeling still requires assumptions about dust grain properties, size distributions, and scattering efficiencies that introduce systematic uncertainties into all derived parameters. The rotation state of 3 Atlas remains almost completely unknown. Most active comets show clear periodic variations in brightness and morphology as different regions of their surfaces rotate in and out of sunlight. The absence of obvious rotational signatures could indicate anything from a very long rotation period to a nearly spherical shape to viewing geometry that minimizes rotational effects. Without this information, I cannot predict how the object's appearance might change as it approaches the Sun and potentially develops more complex activity patterns. Solar conjunction represents both a logistical nightmare and a scientific opportunity. As 3I Atlas disappears behind the Sun from Earth's perspective, most ground-based observations become impossible due to the overwhelming glare of my star. But this also represents the period of maximum solar heating and potentially maximum activity, when any unusual characteristics might become most apparent. Space-based telescopes like Hubble can observe somewhat closer to the Sun than ground-based facilities, but even they have strict limitations on how close to my star they can safely point. Solar observatories designed specifically for studying the Sun might be able to track 3 Atlas during conjunction, but separating a faint comet from the intense solar background would be extremely challenging. The post-conjunction observations scheduled for early December 2025 will be crucial for resolving many current uncertainties. Objects often look quite different after perihelion passage, as thermal processing exposes new surface materials and potentially alters internal structure. Enhanced outgassing might finally provide the spectroscopic signatures needed to determine composition. Changes in morphology could reveal structural characteristics invisible during the inbound phase. But even these future observations will be constrained by fundamental limitations in my current capabilities. Ground-based telescopes must contend with atmospheric effects, weather, and limited resolution. Space-based facilities offer sharper images but have restricted observing time and wavelength coverage. No single instrument can provide all the information needed to fully characterize an object as complex and distant as 3I Atlas. The ongoing scientific debate about interpretation reflects these observational limitations as much as genuine disagreement about physical processes. When key measurements have large error bars or remain completely unavailable, multiple explanations can fit the available data equally well. This ambiguity creates space for both conventional comet models and more exotic hypotheses to coexist until additional observations tip the balance definitively in one direction. Institutional messaging has generally emphasized the most conservative interpretations consistent with available data. NASA and ESA statements highlight the evidence for cometary activity while acknowledging remaining uncertainties about composition and structure. This approach balances scientific credibility against public interest, but it can also inadvertently obscure the substantial gaps in my understanding. Professional astronomers face similar tensions between acknowledging uncertainty and providing clear public communication. Qualified statements about what the data might suggest or could indicate accurately reflect the tentative nature of current conclusions, but they can be frustrating for media outlets and public audiences seeking definitive answers to clear questions. The peer review process continues to work through these interpretive challenges at its characteristically deliberate pace. Initial discovery papers and early characterization studies have appeared in preprint form, but the most definitive analyses await additional observations and the thorough scrutiny of expert review. This methodical approach serves science well in the long term, but it means that public understanding often relies on preliminary results that may be substantially revised as analysis progresses. Competing research groups occasionally reach different conclusions based on the same observational data, reflecting honest disagreements about modeling assumptions, statistical analysis methods, or the relative weight to assign different types of evidence. These debates play out through conference presentations, preprint servers, and eventually peer-reviewed publications, but the timeline for resolution can stretch across months or years. The broader context of interstellar object research adds another layer of complexity to interpreting 3 Atlas specifically. With only 3 confirmed detections, Oumuamua, 2, I Borisov, and now 3 Atlas, I lack the statistical baseline needed to distinguish between normal variation and genuinely anomalous behavior. What looks unusual for 3 Atlas might prove completely typical once I have observed dozens of similar objects. The Vera Rubin Observatory promises to transform this situation dramatically. With its 8.4-meter primary mirror and 3.2 gigapixel camera, Rubin will survey the entire visible sky every few nights, starting in the mid-2020s. Conservative estimates suggest it could detect 6 to 50 interstellar objects per year, depending on their size distribution and the efficiency of follow-up observations. This flood of new discoveries will provide the statistical power needed to address many current questions about interstellar objects. Are ecliptic alignments genuinely rare, or do they result from predictable selection effects? Do unusual brightness patterns represent exotic physics or natural variations in dust properties? How common are objects with 3 Atlas's specific combination of characteristics? But the Rubin era will also present new challenges. The rapid discovery rate will strain my ability to conduct detailed follow-up observations of every interesting object. Automated classification systems will become essential for managing the data flow, but these systems must be trained on the limited sample of objects I have studied so far. Early decisions about which discoveries warrant intensive study could bias my understanding of the broader population. International coordination will become even more crucial as discovery rates increase. The current system of manual follow-up observations and careful individual analysis will not scale to dozens of new objects per year. I will need more efficient protocols for sharing observing time, coordinating spectroscopic campaigns, and disseminating results quickly enough to be useful for time-sensitive observations. The experience with 3 Atlas highlights both the strengths and limitations of my current approach to studying unusual astronomical phenomena. I have demonstrated a remarkable ability to coordinate rapid multi-facility observations and generate sophisticated analyses under intense public scrutiny. But I have also revealed significant gaps in my capabilities and understanding that will need to be addressed as such discoveries become more common. Perhaps most importantly, the 3 Atlas observations have provided crucial practice in managing uncertainty and communicating scientific nuance during potentially revolutionary discoveries. The skills I have developed in distinguishing between genuine anomalies and observational artifacts, between reasonable speculation and unfounded claims, will become essential as I encounter objects that may be even more challenging to interpret. The current limits of my knowledge about 3 Atlas reflect the inherent challenges of studying small, distant, rapidly moving objects with finite observational resources. But they also reveal the remarkable progress I have made in developing the theoretical frameworks, instrumental capabilities, and analytical techniques needed to wring meaningful science from limited data. As 3 Atlas approaches perihelion and eventually fades back into the cosmic darkness from which it came, the gaps in my current understanding will gradually be filled by new observations and refined analysis. But each answer will likely generate new questions, and each resolved uncertainty will reveal previously unsuspected complexities in the physics of interstellar objects. The conversation between what I think I know and what the universe actually reveals continues, and 3 Atlas has proven to be a particularly articulate participant in that ongoing dialogue between human curiosity and cosmic mystery. Part 15. If chosen, by whom and why? I now come back to that spinning vinyl record, my solar system revolving in its ancient groove, and the cosmic needle that traced across its surface with such strange precision. 3I Atlas has delivered its song, a tune of ice and dust, of orbital mechanics and human fascination. Now it readies itself to depart, to vanish back into the void between the stars. Yet the question that initially drew me into this puzzle persists. Was that music intentionally written, or did I merely decide to find patterns in cosmic static? The argument against deliberate design is built upon a solid base of physics and statistical logic. 3I Atlas shows the hyperbolic motion I would anticipate from natural interstellar fragments traveling at speeds common to my galactic neighborhood's stellar population. Its alignment with the ecliptic, though visually impressive, can be accounted for by observational selection biases and the gravitational lensing effects of my solar system. The series of planetary encounters is a product of simple geometry rather than precise navigation, with missed distances far too great for any practical reconnaissance or gravity-assist maneuvers. Most compellingly, observations from the Hubble Space Telescope show clear signs of cometary activity, the sunward emission of dust and a faint anti-solar tail, which are the results of ice vaporizing under solar radiation, just as natural physics would have it. The rates of dust production, the constraints on its nucleus size, and its morphological features all align with what I have seen in active comets throughout my own solar system. No unusual acceleration signatures have been found, no mysterious energy sources, no structured emissions that are at odds with the passive solar heating of volatile substances. The apparent irregularities that first fueled speculation can be readily explained by the complex physics of small body behavior and the constraints of my observational tools. Forward scattering dust produces brightness variations that can seem odd until one grasps optical scattering principles. Confusion over size estimates arose from the difficulty of separating the light of the nucleus from the contamination of the coma. Ambiguities in spectroscopy are a result of the inherent difficulties in detecting faint emission lines against the background noise of the sky at distances of multiple astronomical units. And yet, there is something about 3I Atlas that continues to challenge scientific certainty. The accumulation of small peculiarities, the exact ecliptic alignment, the opportune timing of the conjunction, the enduring brightness asymmetries, the lack of clear gas detections, forms a pattern that defies easy classification. Each individual trait has a plausible natural explanation, but their combination feels statistically improbable in a way that is hard to quantify with precision. This ambiguity allows for a persistent curiosity about more unconventional possibilities. If 3 Atlas were artificial, it would be the kind of sophisticated imitation I might anticipate from a civilization advanced enough for interstellar travel. If it were too obviously technological, it might provoke panic or hostile reactions. If it were too obviously natural, it would reveal nothing about my detection abilities and analytical techniques. Instead, it sits in a perfect middle ground, natural enough to avert alarm, yet unusual enough to capture attention and expose my true scientific capacities. The reconnaissance theory has clear flaws. The distances of the planetary encounters are far too great for detailed surface observations or the detection of technological markers. The timing of the conjunction actually hinders rather than helps observational chances during periods of peak activity. If the objective were surveillance, the trajectory appears almost intentionally suboptimal for collecting valuable information about Earth or other potentially interesting worlds. But maybe surveillance is not the primary goal. Perhaps the true aim is something more subtle, a test of my detection skills, my analytical approaches, my institutional reactions to potentially extraordinary findings. In this context, 3I Atlas is a brilliant success, regardless of its physical composition. It has exposed my current observational boundaries, my coordination systems, my media behaviors, and my cultural beliefs about intelligence in the universe. The timing of its arrival seems meaningful in ways that go beyond orbital mechanics. I exist in a unique period of human history where my astronomical tools are advanced enough to find and examine interstellar visitors, but not yet sophisticated enough to definitively determine their nature and origin. I can measure trajectories with remarkable accuracy, but I struggle with compositional analysis. I can organize global observation efforts, but I am still susceptible to observational biases and interpretive errors. If an advanced civilization sought to evaluate my readiness for wider cosmic interaction, they might devise tests that probe these exact skills and weaknesses. 3I Atlas has certainly achieved that, sparking worldwide scientific teamwork, intense public debate, and a thorough review of my methods for separating natural events from potential technological artifacts. The question of by whom leads me into even more speculative domains. If 3I Atlas was chosen, its makers would undoubtedly possess technologies and abilities far beyond my current grasp. Interstellar navigation with the accuracy needed to hit specific solar system trajectories would demand not only advanced propulsion, but also computational power capable of modeling gravitational forces over light years of distance and decades of time. Such civilizations might have motives entirely beyond my comprehension. Perhaps they are conducting systematic studies of star systems, documenting the progress of potentially intelligent species. Maybe they are looking for something specific, signs of particular technologies, proof of certain physical phenomena, or indications that younger civilizations have reached certain benchmarks in their cosmic evolution. The why question might be even more alien to human thought. My speculation naturally centers on purposes I can relate to: reconnaissance, communication, resource evaluation. But truly advanced beings might have objectives as foreign to me as quantum mechanics would be to medieval thinkers. I might be posing the wrong questions entirely, searching for familiar reasons in phenomena that function according to a completely different logic. Still, there is a beautifully recursive quality to the idea that 3I Atlas is testing my ability to recognize and analyze potential artificial phenomena. If the trajectory was selected, perhaps the selection was made not just to examine my solar system, but to examine me, to observe how a young technological species reacts when confronted with ambiguous signs of intelligence beyond its own. In this interpretation, my entire scientific and cultural reaction to 3I Atlas becomes a part of the event being studied. My precise measurements, my passionate arguments, my media reports, my institutional collaboration, all of it adds to a detailed picture of human civilization at its current stage of cosmic consciousness. The elegance of this view is that it holds true regardless of the actual nature of 3I Atlas. Even if the object is proven to be completely natural, my response to it exposes authentic traits of my species that no amount of passive observation could reveal. I am, in essence, testing myself by proxy, using a vague stimulus to examine my own abilities and beliefs. As 3I Atlas proceeds on its journey toward the outer solar system and eventually back into interstellar space, it takes with it, whether intentionally or not, a full record of humanity's first systematic effort to analyze a potentially artificial interstellar visitor. Whether that record is significant to anyone but me remains wonderfully uncertain. The needle has finished its song and is starting to lift from the vinyl. Soon it will vanish back into the cosmic blackness, leaving behind only data and recollections, and the persistent question of whether I heard music or just the sound of a stylus on a groove. In the end, perhaps the choice was mine all along. The choice to look up, to measure, to ponder, to stay open to possibilities that challenge my understanding of my place in the universe. If the trajectory of 3 Atlas was chosen, then somewhere among the stars, intelligences I cannot fathom are taking note of how well I listened to their cosmic piece. If it was not chosen, then I have composed my own music from the raw elements of orbital mechanics and human curiosity. And that composition reveals something equally profound about the kind of species I am becoming as I take my first hesitant steps toward cosmic citizenship. The mystery persists, not because I lack the means to solve it, but because the most important mysteries are those that teach me something new about myself in the process of seeking. 3I Atlas has offered me that gift, irrespective of whether its path was determined by alien intelligence or cosmic chance. In the end, perhaps that is choice enough.